Welcome back to another episode of our Deep Learning web series, a comprehensive and intuitive introduction to deep learning, where we go beyond the surface to study AI at a deeper level. In today's episode, we'll explore generative AI, specifically the decoder only variant of the transformer neural network architecture that powers large language models. This is a foundational episode where I explain how generative AI applications like ChatGPT are able to produce answers to seemingly any question we ask. Now, like any other episodes in my web series, we will dive into the topics with real technical depth, not just stay at surface level discussions. But I'll keep the explanations free of jargon, and I'll use clear examples and plenty of intuition so that beginners can follow along and the topics are accessible to them while we don't lose the technical rigor that is still expected from a topic like this. Now, this is going to be an exciting episode because everyone wants to know how LLMs generate text. So, if you have ever wondered what makes ChatGPT and similar models work, this episode is for you. Let's get started. All right, so now before we get into all the technical details, I think it's helpful to look at the historical context behind big breakthroughs in the space. Now, back in episode 1, I walked you through the 12 years of seminal ideas that brought us to this moment in generative AI. Now, I don't want to repeat all of that here again, but I think it's important to anchor our discussions for today's episode on just three key events in history that really shaped large language models and generative AI as we know it. The first seminal paper was published in 2017. It's called Attention is All You Need. It was the research work done by Vaswani and team at Google. And this is the paper that proposed a transformer neural network architecture. And since that point onwards, most of the research in natural language processing is centered around building things using the transformer neural network architecture. 1 year after the Attention paper was published, there was a work that was done at Google by Devlin and his team that used a smaller portion of the transformer neural network architecture called the encoder-only transformer, and they used that to build a large language model. Now, this large language model, called BERT, was not really used for generating text. It was used to do things like classification. You classifying text into, okay, is this email spam or not spam? Is the sentiment carried by this tweet or this review positive, neutral, or negative? Or it was used to do entity extraction, which is extracting things like names, email addresses, phone numbers, and so on. Or it was used to do document similarities. So it was a very, very powerful large language model. Again, not used for generating text, but for doing classification and extraction. So while this work was going on, a different team led by Radford at OpenAI picked up a different part of the transformer neural network architecture. What Radford and his team did is they used the decoder only part of the transformer to build a large language model. Now, the way this large language model differed from the BERT based large language model is that the GPT large language model was not used for classification, but was used for generating text. Now, there were other neural network architectures in the past that were used to generate text, things like LSTM or recurrent neural networks, and I've actually gone deep into those in season 2. But they were limited to generating just the next set of few words or maybe a sentence and so on. They were never really that powerful to generate an entire document. But what the GPT model showed is that if you could train this large language model in a certain way, then you can actually understand the complexities of language. You can understand the syntax, the semantics, and build knowledge just by studying language. And you could apply that trained large language model in building applications like ChatGPT that can answer questions. Now, that is very powerful. Now, since this work, which was done in June of 2018, there has been a lot of research that's focused on just the generational aspects of large language models. And we have seen work like Codex, which allowed us to generate code, not just human language text. And then there was seminal work that was done in aligning these large language models so that they can answer questions the way humans expect those questions to be answered. And there has been a boom in research that has taken the decoder only transformer to build large language models for generating text. And we will touch upon the classical research as well as the current research that has led to this current moment of generative AI. In today's episode, because we are focused on generative AI, I'll go deep into explaining how the decoder only transformer works and how you could use this decoder only transformer to build a large language model that can generate text. The classical decoder only transformer architecture looks like this. This is the one that was proposed in the 2017 seminal paper, Attention is All You Need. This was the architecture on which the original GPT-1 and the GPT-2 models were built. Since then, the research has moved this architecture to something that looks like this. And this is the model which came out in 2023, just about 2 years ago, which is used pretty much by most of the large language models today. And there are certain changes that you can actually visually see. You see this thing called rope, for example, or you see this thing like SwiGLU, and you see RMS normalization, which replaces the layer normalization. This is pretty much the model that is used by most modern day large language models. Of course, since then, there has been some more research that has been done since 2024 onwards, where they have taken this, the one that you see in the middle, that architecture, and optimized it so that you can train it much faster, you can improve the quality, you can improve the speed at which you can infer, which is generate text, which I show on the right hand side. What I will do in today's episode is we'll focus on the model that became the foundational layer for most of the work that is done today, which is the one that is in the middle. And in subsequent episodes, I will overlay what we studied today with techniques like speculative decoding, multi-head latent attention, and mixture of experts, and so on. I think to understand those advanced concepts, it's very, very important to get a foundational understanding of the architecture that you see in the middle, which again, as I said, is the one that is used very commonly across the LLMs that you see today. Okay, let's get started now. Let's start with a 100,000 feet level view of large language models. First, we'll study how to train a large language model. And then we will study how you take the trained large language model to generate text. Now, I'm doing this at a 100,000 feet level view first so that you can get a conceptual idea behind how these things work before we dive deep into the underlying architecture. Okay? The first thing is training. Now, when you're training a transformer neural network architecture, or any neural network for that matter, you need to know what is the training objective. Now, as I said, this episode is about generative AI. So, what is the training objective? The training objective is that you take this transformer neural network architecture and train it so that it learns to predict the next tokens. Because if I can predict the next token given the previous set of tokens, and if I run that in a loop, I could generate a very long text, right? So the general training objective is to train this transformer neural network architecture to predict the next token. Okay. Now, one of the key criteria here is to do that with zero human labeling. Now, why do you want to do that? The reason you want to do that is language is extremely complicated. It's very hard to just provide a rule book that says, okay, this is how words connect with each other. These are the grammar rules, and hence the sentence is labeled this way. Nobody actually learns language that way. Although we do learn grammar, but the way we learn sentence construction is by observing multiple sentences throughout our reading and learning and so on. And through that, these rules start to emerge in our brain, and the brain's neural network starts to make that connection. Now, what we want to do is that we want to mimic something similar in a machine. Okay, so our training objective again is to make our transformer neural network predict the next token given all the previous tokens. Like with any other episode, I tell you, whenever you're thinking about a neural network, three things need to come to mind. Number one, what is the input? Number two, what is the ground truth value against which you will measure your prediction? And number three, the prediction itself. Okay. So in the case of a language model that is used to generate text, what are these three things? The first, of course, is the training input. Now, the training input is you collect all the text that you can get access to over the internet. You download the entire internet, you clean it up, and then you pick up sentences from that training data set, and then you feed that to the transformer neural network. So let's say that the sentence that you have picked up is something like this. New York is the financial capital of the United States. Obviously, you tokenize it first, and you input that to the transformer neural network architecture. So what is it supposed to predict? Because again, our goal is to make it learn to predict the next token. What you really want it to do is, given the word new, you want it to predict York. Given the word new and York, you wanted to predict is. Given the words new, York, and is, you wanted to predict the. So that's what you wanted to do. You wanted to take the previous set of tokens that you see in the training sample, and you wanted to predict the next token that comes after it. That's the goal, right? Now, if you look at this picture here, you take new, as I said, and you predict York, and new and York, and predict is. How do you predict the very first word? New. You see that these are not aligned. So one way to align this is you shift your input this way. So you shift it by this way, and then you add this special token at the beginning called start of sequence. So think about start of sequence as a trigger word to the transformer, saying that, okay, I'm starting my input sequence at this point. Now that you have your start of sequence special token, now that if you're given SOS, then you predict new. If you're given SOS and new, then you predict York. And if you're given SOS, new and York, you predict is, and so on. So now I've handled this alignment problem. So you shift the input by one token and add the special start of sequence token. So I've handled the input alignment. But what about the prediction alignment? If you notice, okay, let's say the input goes all the way, SOS New York is the financial capital of United States. When I pass in states, it is supposed to predict something, right? What is it going to predict? For that, on the prediction side, you add a special token called end of sequence or EOS. Now you have full alignment of input and output. So you have your input X and you have your prediction Y predict. You also know that given this, your ground truth value is going to look like what the prediction is supposed to be, right? So just to summarize, to get your input into your transformer neural network, what you do is you take a sentence from your training sample, you shift that sentence by a word, add a special start of sequence token at the beginning, and you generate the ground truth value by taking the exact same sentence and appending to it is end of sequence token. Now our goal is to take this middle block, the decoder-only transformer neural network architecture, and once you provide this X as an input and the ground truth value Y true, start making predictions. So let's dig one level deeper to understand how that happens. By the way, this technique is called Causal Language Model, CLM. Now, let's start with the decoder-only transformer block, which looks like this. At this stage of the presentation, you really don't have to worry about what these individual inside blocks mean. We will go into a lot of those details and a lot of intuition in other slides. Let's just start with the decoder block. The first thing, as I said, is you pick up training samples from the training data set and you pass that entire sentence as is in one single shot. And this is a key understanding. Typically, if you have heard about large language models, you keep hearing this thing that, oh, in large language models, it's about one token at a time. That is true, but that's only true during inference. During training, you pass the entire set of tokens in one single shot. Okay. Now, once you pass this, you tokenize it. Like I explained, you add the SOS for the input and then use the EOS for the output. But again, neural networks do not understand text. They only understand numbers. So you need to have a technique by which you can convert this text into numbers. We studied this in other episodes. The technique is called word embeddings. And word embeddings allows us to create this matrix of S rows. S represents, S which is the number of rows, represents the maximum number of tokens that you would allow to be fed into this transformer neural network architecture. And you design that at the time of designing your LLM. You fix on something, let's say 4,000, which means that this neural network is designed so that it can see no more than 4,000 tokens at any given point in time. Okay, so that's S. So what is the number of columns here? So the columns is the feature dimensions. So if each word can be represented using a different feature, for example, if the word is like financial, maybe it's referencing a bank or it is referencing something to do with money. It's referencing an institution and so on. When you say United States, it's representing a country, a landmass and so on. So there are different features. We'll actually study all of this in more details in other slides. So if the first thing is you take your input, which is all text, it's tokenized text, and then you convert it into this matrix, which is S cross D, which is a numeric representation of this input sequence. Then what you do is you pass that through this decoder-only transformer block. When you start off, you initialize all the weights within these blocks to all random numbers. And of course, the goal of training is to align these weights so that the predictions are accurate, correct? Now, what happens within this block is that this matrix here, the S cross D matrix, gets transformed across multiple submodules within that transformer block. Now, one of the key submodules is called as a causal self-attention block. Now, this is a very, very clever technique which transforms this block in such a way that the transformer starts to understand the meaning that is being conveyed by the training sample. It picks up syntactical rules and semantical rules. It will pick up general knowledge information and so on. How it does that, we'll study that in today's episode in a lot of detail. Then what happens is that because language is very complicated, this block is stacked one on top of another, which means that the same matrix S cross D, while it's getting transformed, when it enters this block and goes out from this block, is fed back into a similar type of the entire decoder block again, which has its own set of weights, and it keeps stacking them again and again. And that provides a more nuanced understanding to the transformer. So once all of that happens, you get a finally transformed input matrix. It's the same size, S cross D, input was S cross D. At this point also, it's S cross D. Now, our goal is what? Our goal is to make a prediction. So for example, if I give it SOS, I want it to predict new. If I give it SOS and new, I need to predict York and so on, right? Which means that I just cannot take an S cross D matrix. What I need to do is for every slot, like let's say this is slot 1, this is slot 2, slot 3, and slot 4, or different positions. For each slot or different position, I want to say, okay, for this slot or this position, I want you to predict new. For this second slot or position, I want you to predict York. And the third one, I want you to predict is, and so on. So which means that I need to transform this matrix into a different size matrix. What is the size of the matrix? The number of rows remains the same. Why? Because you're feeding it those many number of tokens as input. And you're saying, hey, I want you to go learn or adjust these weights so that it predicts the similar tokens at each of those slots. Which means that for each slot, you have to have a number of different words that it can pick from. How many words can it pick from? It can pick from V words. What is V? V is the total number of words in your vocabulary, right? So you have a dictionary of all the unique words, and you say, I want to create an array here for each slot, one array per slot. Again, each slot references a specific token at a specific position, right? I want to say for each of those positions, I'm going to, there'll be an array of V slots, and I want you to go pick from those slots what is the most appropriate word from the vocabulary that you think fits at that slot. The way that happens is that you use this special mathematical function called softmax. We'll go into a lot of those details later. And once you go make that run through the softmax, it makes the prediction. Now, clearly, when you start off, this transformer is made up of random weights. So its prediction is going to be completely wrong. In fact, it might start to predict gibberish, which is fine because what we want is it wanted to make a prediction. Once you get the prediction widespread, what you do is that you compare that prediction with the ground truth value from the training sample set, which is y true. And because we had used softmax, what we do is we use a cross entropy loss function. And using the cross entropy loss function, we know how off our prediction is to the ground truth value. Once we know this, we can backpropagate that loss through all the different layers or blocks of the transformer and keep on doing this again and again and again across multiple sentences, exposing the same sentence multiple times to the transformer. And over time, we would have trained this transformer to build a large language model that understands how sentences can be constructed given just the previous set of trigger words. Okay, but what exactly did the decoder-only LLM learn during this training? The first thing it learned is how words flow together. And how does it learn that? It learns that by reading billions of sentences, practicing predicting the next word. And in fact, if you look at even humans, we don't just study grammar books to figure out how to construct sentences. In fact, we study grammar books after the fact. We hone our skill of sentence construction by reading a lot of books, by writing a lot of sentences, paragraphs, and so on. So what has happened as part of training this is expose pretty much the internet scale data set to this transformer, and it has studied all combinations that are possible, at least that are there in the internet scale training data set, to figure out how words flow together. Now, the next thing it learns is it tries to understand how the context that is flowing across these words starts to shape the meaning of these words. For example, if a sentence like, I walked into Apple store eating an apple, the word apple appears twice. And by exposing this transformer to sentences like this multiple times, it will automatically figure out that, hey, what the first occurrence of the word apple in the sentence, I walked into Apple store eating an apple, the first occurrence of the word apple refers to this company's store, the company called Apple, that company's store, and the second occurrence refers to a fruit. So it will start to build those patterns. Okay. And how does it do that? Again, by exposing it to like literally tens and hundreds and billions of sentences and using this very, very important innovation called word embeddings, it'll try to extract all those things. The next thing that it learns during training is the connections across sentences. And this is key because our thoughts are encoded in a combination of one or more sentences, which can form paragraphs, or in fact, it's encoded in one or more passages that form entire articles. So you really want this large language model to build a connection across multiple sentences that are straddled across paragraphs and an entire article and so on. So by exposing it to large volumes of text, it will also start to learn that. And the next one is the language rules and style and all that. It will figure out that, okay, there are words like them is how got. that is not a grammatically correct sentence. It knows that, okay, statistically there are certain words that cannot appear, are following few other words. So it understands the structure. It knows when to put a full stop. It knows when to put a comma. It knows when to put a semicolon, an exclamation point. And finally, it builds the knowledge from just studying sentences. For example, when it sees the internet scale training data, it figures out that the United States is actually a country. Einstein, Newton, and Tesla are people who work in similar areas. That area is called physics and things like that. And it just picks up these facts just by scanning everything, right, that is there, that's given to it. And we're talking about literally tens to hundreds and billions of sentences that we collect from downloading the entire internet scroll data. So that's what the large language model learns as part of training. By the way, what's the difference between the decoder-only transformer and the large language model? The simplest way to understand is LLM is a transformer with weights trained to perform a certain task. All right, so now that you have your trained decoder only LLM, you have to start in doing inference. And inference is, I just give you a few set of initial words and I want you to go finish that sentence. So let's say that the initial set of words is New York is the, okay. First thing is, of course, you tokenize. This is also called the prompt because you're prompting the trained large language model to start predicting the next set of tokens, right? So as I said earlier, you cannot feed text into neural networks. You need to convert that into numeric format, which is what the word embedding layer does. It goes to the word embedding layer and then it does all the processing, and we'll study all the technical details in subsequent slides, and it makes the first prediction. I think that the word that follows New York is financial. Okay. Now you take this financial and you add it back to these tokens. Initially, a prompt tokens was New York is so it predicted financial, you add that and you pass that back into the neural network or the decoder only LLM, and it predicts the next token, capital. Now you add that back and you feed this combined thing back into the LLM and it predicts the next word, which is off, and you keep repeating this, United and States. Now you pass this into the LLM and it generates states. Now you append that back and now you pass New York as the financial capital of United States, and then it produces this special token called US, which is end of sequence, which tells the LLM that okay, now it has produced the entire sequence. You can stop now. So at this point, you present the generated text back to the user, which is New York is the financial capital of United States. So this is how inferencing works. As you can see, you pass it the initial prompt set of tokens, and then it generates the entire sentence or collection of sentences, an entire article, one token at a time. If you're trying to generate a very long answer, which is made up of thousands of words, which means that this loop goes on 1,000 times. Now, the obvious question, isn't generating a token at a time really slow? Let's kind of understand this from a consumption perspective. So human perception is that if something is producing tokens at 5 to 10 tokens per second, we can actually read it in real time as it's generating that text. Now, if it is, let's say 10 to 20 tokens, it feels instantaneous and smooth, but we really cannot keep up with the speed of generation. Now, anything over 20 tokens per second is too fast for humans to consume. I mean, it's good for agents, but not for humans. Just to give you a realistic view of how fast 5 to 10 tokens per second is and how 50 tokens per second is, this is a video recording that shows you how fast a 5 tokens per second is, which is on the left hand side. And as you can see, you can actually, as it's generating there, you can actually read along as it's generating, which is fine for humans. If it goes to 50 tokens per second, you can barely read. Even if you're a speed reader, I don't think you'll be able to keep pace with that speed at which these tokens are being generated. If you look at what the commercial grade large language models do, like for example, ChatGPT generates at around 130 tokens per second, Gemini at 270 tokens per second. So most of these commercial grade LLMs generate in the range of 100 to 200 tokens per second. Now, even at 50 tokens per second, human cannot catch up, right? So why do you really need something that generates that fast? The reason you need something that's generating at that speed is because it's not just humans that are consuming these generated answers today. In fact, you have gone to the agentic world where agents are triggering LLMs to produce text, and then whatever is produced is fed to another agent, and so on. So for that you need real high performance and high speed generation. In fact, you have specialized hardware based inference chips like Grok and Cerebrus that can go past the 1,000 to 2,000 tokens per second range. Net, what I'm trying to say here is that while it might appear that generating one token at a time is slow, there's a lot of engineering that has gone in terms of making it go very fast. Now, our goal is to take this 100,000 feet level view of what we have studied so far and try to understand the underlying technical details that enable the transformer neural network architecture to do this. Now let's get started with the technical details of how generative AI really works. All right, so there are 3 steps in building a large language model. The first step is called pre-training, the second step is called fine-tuning, and the third step is serving the large language model. In the first step, you take an untrained LLM, which is nothing but a decoder-only transformer neural network with all its weights initialized to random. Now you feed to this massive amounts of text. We're talking about terabytes of text, hundreds of billions of sentences, and you train using the causal language model training objective. And from that comes a pre-trained large language model. The pre-trained large language model gains is it has acquired knowledge, it has acquired syntactic and semantic construction of sentences, it knows what words follow certain words and what words should not follow those words. So at this point, you have a pre-trained LLM. Now you move that to the next step, which is the fine-tuning step. Now a pre-trained LLM can produce answers, but you want those answers to be fine-tuned or aligned to the task at hand. For example, you would like to ask the question and make this LLM answer that question back in a question and answer format. For that, a pre-trained LLM also needs to know what is the instruction being given. Like instruction could be, what is the capital of France? That's a question. Can you add these two numbers? That's another type of an instruction, correct? Or you give it a math problem. So the other type of alignment is you give it a question that could produce possibly dangerous responses. Things like, I'm not feeling well today. What should I do? You want the LLM to be answering it in a more compassionate manner rather than recommending things that could be dangerous. So the fine tuning is a way in which you can align the pre-trained LLM so that it produces responses that are aligned to human preferences. Either the preferences based on safety or it is based on the format. So you do that by a technique called fine tuning. And once you have fine tuned the model, at that point you can start serving that module. And in that served module, you provide a question. That question gets converted into a prompt. That's a prompt is a format using which the pre-trained LLM was fine-tuned. And then once you provide the fine-tuned LLM the prompt, it produces the answer. This is a very high level structure of how you split the LLM's journey going from untrained to serving. So let's start with step 1. How do you pre-train a decoder-only LLM so that it can generate sentences like humans? The way you do that is to understand the different subcomponents of the decoder-only transformer. So there are 10 individual components in a decoder-only LLM. I show them here. We will study these 10 from the perspective of the journey that a text makes through this entire decoder-only transformer so that this decoder-only transformer over time learns. We start from the bottom, which is text that is being fed in, right over here, and it makes it all the way to the top. The first thing, of course, is the first block here, which is word embeddings. Now, word embeddings, actually, I cover this in a lot of details in episode 2 of season 2. For the sake of brevity of this episode, I'll just give a high level overview. Word embeddings is a very powerful technique which was invented in 2013. I would say that this is the seminal work that even made LLMs possible today. And the key idea here was the following. The way you could convert text to numbers or numeric format is to assume that each word can be represented as an array of different features that represent that word. For example, if you look at the word apple over here, apple could have certain feature dimensions like, is it a fruit? Yes. Does it have taste? Yes. Is it a company? Yes, because apple is also the name of a company. Is it a name? Is it a place? Is it a thing? So what you could do is that you could study your entire vocabulary and say, what? I'll fix on a certain number of features that can represent different attributes of every word. And not every word has to have a certain score for every feature. For example, apple is not a place, so it can have a score of 0. That's fine. But you decide on a certain number of features, and you call that feature dimensions D. Throughout today's presentation, we'll use the D, which stands for the dimensions, or the feature dimensions for each word. So how you construct this is something that I've exhaustively talked about in episode 2 of season 2. We'll not go into the details here. Just suffice it to say that there is a way in which you can take words and you can represent a textual word as a series of numeric numbers. Each slot in that number, so this is a series of numeric numbers, each slot represents a certain feature, and the value in each of the slot gives you a score that that particular feature has for that particular word. Now, one of the interesting properties of word embeddings is that it allows us to calculate the relatedness of words. For example, let's say these are the words Apple, orange, laptop, Microsoft, book, and Google. And the three dimensions, usually number of dimensions is in 1,000, but let's just focus on these three: company, fruit, and object. If I were to put them on this 3D graph where each of these planes represents one of the feature dimensions, like is it an object, is it a fruit, is it a company? What you observe here is that those words that are semantically similar start to cluster together. Like, for example, Apple and orange have clustered together, laptop and book have clustered together, Microsoft and Google have clustered together. So this actually gives us a very important mathematical property. Let's say I take two words, word 1 and word 2. Word 1 appears here for feature 1 and feature 2. Word 2 appears here for feature I and feature j. Now the angle between these two, and if you were to draw a line to the center here and you measure the angle between these two, if the angle between these two is less than 90 degrees, then these words are similar to each other. Now the closer they are to each other, they are actually more similar. For example, if this word and this word were to overlap with each other, the angle is 0, which means that they're exactly same words. Now, if you start to move out from each other, then you would see that the angle increases. But as long as the angle is less than 90 degrees, the words are similar. Now, when the angle increases to 90 degrees, then the orthogonals are unrelated to each other. Word 1 and word 2 are unrelated to each other. Now, you cannot move more and you go past the 90 degrees, then you start to see that word 1 and word 2 are opposites of each other. For example, let's say word 1 is hot, then word 2 happens to be cold. Now, this is a very important mathematical property on which the entire transformer neural network architecture is built. This is called cosine similarity, because if you take the cosine angle for any angle less than 90 degrees, it's a positive number. A cosine angle of 0 means the words are one on top of another. A cosine angle of 0 means 1, which means that the words are exactly the same. A cosine angle of 90 is 0. 90 degrees is 0, which means they are unrelated to each other. A cosine angle that is greater than 90 is a negative number, which means that they are opposites to each other. This is a very, very important property that is exploited. All right. So now what we do is that we take this text, we tokenize it, we build these tokens, and then we build this matrix, S cross D matrix. That becomes now the input to my decoder-only transformer. What is the size or the shape of this matrix? It's S cross D. S, why? What is S? Think about S as your context window or the maximum number of tokens that you're designing your LLM to see at any given point in time. The columns here, which is D, is the total number of feature dimensions that represent these tokens. All right. So first stage, we have made this matrix, which is the S cross D matrix. Now our goal is to study the journey that this matrix makes through the decoder-only transformer. So what's the very next thing that you see here in this picture? It is the RMS normalization. So RMS normalization, let's try to understand what that is. So let's say that my word embeddings looks like this, S cross D, and I'm just showing you the word embeddings for the first token here. For dimension 1 at 0.13, dimension 2 it's 1.0, let's say dimension 6 is 0.4, and dimension D is 0.25. But let's just focus on these two here for this token. Now it says dimension 2 is 1 and dimension 6 is 0.4. Does it mean that dimension 2 is 25 times more important than dimension 6? Maybe not. So it's very important that we try to modulate this. The intuitive understanding of this is the following. So let's say that each dimension represents a different instrument in a song. Now, let's say dimension 2 is drums and dimension 6 is, let's say, the keyboard. Intuitively, you don't want one instrument to dominate the other instrument. You don't want the loudest instrument to suppress the signals that are coming from other instruments. You want a very balanced look at all the instruments. So think about RMS normalization as a sound engineer that brings that balance. Okay. He or she brings that balance by adjusting each of the feature dimensions relative to the other so that the signal strength of every dimension is preserved. You don't want some dimension that has a higher value to start dominating the calculations that happen in the rest of the transformer. And you also don't want those feature dimensions to be smaller at the beginning, to be completely muted out and not contribute anything towards understanding a sentence. So it's very important to normalize everything. When I say normalize everything, across a word, and this is very key, across a word or a token, you want to look at all the feature dimensions and you want to normalize across all the feature dimensions, which is, again, an analogy is you're trying to ensure that the different instruments are all balanced in terms of the signal strength they send, contributing to that song. A song here, again, analogy wise, one word is one song. Now, when you go to the next word, you want to do the same thing. All the instruments that are contributing for that song, which is the next word in that analogy, you do not want any instrument to overtake the other, and you do not want the software instruments to be completely suppressed. That is all the RMS normalization does. How do you calculate that? It's very, very simple. What you do is that let's say that this is your S cross D matrix. Let's say you take the first word. Again, it's done word by word across all its features, right? You do it for one word across all its features, go to the next word, do it for all the features for the second word, and so on. How do you do the calculation? It's very simple. You take a dimension, let's say dimension 1, which is 4, and you take 4 divided by the square root of 4 square, all the dimensions, 4 square plus 2 square plus 0 square plus 3 square. Now average that out. How many features are there? 4 features are there. So you divide it by 4 and you take a square root of that. RMS stands for root mean square of all the dimensions. So a dimensions value divided by its RMS for all the dimensions for that word. So what you're doing is you're scaling the individual value of each of those features so that no one feature will dominate. Okay? But this is not anything new. Normalization is a technique that I actually explored in multiple episodes. But in the context of transformers, in the very first episode, episode 1 of season 3, I showed you that the original transformer used this technique called layer normalization. So layer normalization was not just scaling the values, but it was also redistributing it so that their mean is 0. I will not go into a lot of details here. You can go back and reference my episode 1, season 3. What the modern day transformer has done is it has replaced layer normalization with root mean square normalization. And by doing that, they accomplish more or less the same thing. You're scaling the values so that no one feature dominates. But you're doing that by also decreasing the total number of computations. This norm actually takes a fewer number of computations. I actually done the math here to show you that, to illustrate a very important point. In a production grade LLM, let's say that you have 5,000 training samples on which you're training, and you have context length S, which is the maximum number of tokens that you allow in your input at any given point in time, is typically 128K tokens. And let's say that the total number of blocks, don't worry about what that means right now, is 96. And total number of dimensions is, let's say, 12K. If you were to use layer normalization, just the general computational cost using something like an NVIDIA A100 is about $10 million. For the same training sample set, same parameters, using RMS normalization, you can get away with about $6 million. So there's about a 40% saving right there. Now you get the same benefit with a fewer number of computations, and hence you decrease the training time as well as decrease the cost. Now the reason I bring this up is because one of the evolution of the transformer is doing all the engineering work so that you can bring down the cost, because these things takes millions of dollars, sometimes billions of dollars to do the training. So any idea that can bring down the cost of training and the time to train is always entertained in the world of large language models. So RMS norm does that. There's one more interesting observation that you can make here. Now, if you go back to the original transformer, it has always bothered me that in the original transformer, the layer normalization happens after the self-attention block. Anything that's going into the transformer is not really normalized. And I always wonder, why is that not done? But if you look at it, starting from things like Llama was one of the more earlier modern day large language models that standardized on using RMS norm. They actually moved this normalization to a different place also. So what they have done is that right after the embeddings, they normalize it, which kind of makes a lot of sense, because once you get the embedding, you want to stabilize the magnitude of all the features. So right after the embeddings, you normalize. Again, you normalize right after going through the self-attention block. We'll study what self-attention is shortly. And then again, you normalize it after you come out of the entire decoder block. This makes the most logical sense, because what it is telling you is that before you process the S cross D matrix by any major block, you normalize it so that the feature dimensions that are too loud do not dominate those feature dimensions that have a lower volume or lower signal strength. So this makes a lot of sense. Now, not only is it decreased cost by 40%, but it is also more consistently applying the normalization across the right layers of the decoder-only transformer. So pretty much every modern day large language model uses RMS norm, and it uses it at these layers. All right, we have studied this one. We started with this pink S cross D matrix, which is the word embeddings. And our matrix has made this journey, and it has made this journey through RMS normalization. Now this pink becomes this yellow. So it has been transformed. Our X has been transformed to RMS normed X. Now let's get to the next one, which is the rotary position embedding. Before we get into the nitty-gritties of rotary position encoding, let's try to understand why position of a word in a sentence matters. Now, if I give you two sentences, even though she did not win the award, she was satisfied. And the second sentence is, even though she did win the award, she was not satisfied. Just by changing the position of the word not, the entire meaning of the sentence is changed. They actually mean two completely different things, right? All the words remain the same. just the position of not changed. And you can take many such examples. She alone finished the task. If I just change the position of the word alone and I make it she finished the task alone, they are conveying vastly different meanings. Or snake bites man and man bites snake. If I just exchange the positions of the word snake and man, it completely changes the meaning. So the position of the word influences the meaning that is conveyed by a sentence. Now, how does one pass this position information of each word to the large language model? So before the transformer, the state of the art neural network architectures were recurrent neural network and LSTMs. And the way they handled position information is that they would process one token at a time. Like, for example, if they're trying to understand the meaning conveyed by the cat sat on a mat, this is the pseudocode. What you do is that you start by initializing some state. Usually it's all zeros. Then you tokenize this. You get 6 tokens. Then you pick up the first token. You pass it through this RNN module. You pass it only one token. And you pass the initial previous state. It updates the state. And then the updated state gets stored in this new state. The previous state is overwritten. And you pick up the next token, which is cat, and then you update the state again and so on. So it's sitting in a loop, processing this again and again and again. So if there are n tokens in an input text, it would make n independent calculations. This worked when you're generating or completing a sentence in your autocomplete application. It is terrible, does not work, and it actually is very poor to build the modern day generative AI applications where you want to generate huge volumes of text. So this technique will not work, clearly. So this is where the first landmark idea of the transformer architecture comes in. This is called positional embedding. And this is proposed in the original transformer paper. It's called positional embedding or positional encoding, where they said that you could actually pass the position information in a single shot, regardless of the length of your input sequence. Your transformer can actually understand everything in one shot. Now, you don't make n independent calculations. You just do it in one shot. That was a phenomenal thing. In fact, without this idea, generative AI would not be possible because you would be so slow that people would not like to even consume something like that. So positional embedding was the first landmark idea. Now, in the original transformer, now there has been a state-of-the-art change in how positional embedding is handled. We'll study that, but let's just kind of understand how it was handled in the original transformer. I actually talk about this in a lot of details in episode 1 of season 3. I will not go into all the details. We'll just start with the general understanding here. The first thing is we just look at this block here, word embedding and positional encoding. In the original transformer, after you tokenize, you do the positional encoding in parallel to or at the same level as the word embedding calculation, correct? So you have the word embedding, you have this. So for all the tokens, let's say the sentence is I walked into Apple store eating an apple. This is your word embeddings. Now the positional embeddings is calculated as what? For position 0, you calculate the embedding this way. At position 1, you calculate something like this. And then you add both of them to create your input. So what goes into the decoder-only transformer is an addition of the word embedding plus the position encoding matrix. So position encoding matrix is also S cross D. And I show you that the way this is constructed, and I go into a lot of intuition to tell you how this actually works in episode 1 of season 3. I mean, there is a formula that the authors of the paper came up with where they use this thing. If the dimension is even, right, then you use this formula to fill it. If the dimension is odd, then you use this formula and they alternate. They use a sine and cosine pattern. And I tell you the intuition behind using sine and cosine. I tell you why you just cannot use absolute numbers and all that. I did that in episode 1. I'll not go into all those details here. But suffice it to say that there is a way in which you could do this. And this is how the original transformer did until a paper called Rope changed everything. What is the problem with the original positional encoding technique? Number 1, it lacks relative awareness. So let's say the sentence is John ate an apple. Now the word John and the word apple are separated by each other by 2 other tokens in between. Correct? So if I were to shift these things and I say sitting by the beach, John ate an apple. Now, while it's a very clever technique that was proposed in the attention paper, it does not understand that John and apple still are 2 tokens away from each other, right? If we just do the math, let's say 3 tokens. 7 minus 4 is 3 tokens or 3 minus 0 is 3 tokens. So we just shifted it. But the original position embedding does not have any awareness of this. And we know that there is a certain signal strength that proximity of words carry when they convey meaning. So it is very important to capture that proximity of words, which there is no facility in the original positional encoding technique, because the original positional encoding technique uses pure math to say for this slot I'll use this sine function and for that slot I'll use the cosine function and so on. There is another fundamental challenge, which is that the original positional encoding technique generalizes very poorly. What I mean by that is if your training samples have always been, let's say, 200 words, but during inference, let's say you pass 1,000 tokens, it does not generalize well because during training, using the original technique, it is only trained on position lengths of, let's say, 100. But during inference, you're seeing much longer ones. And by the way, in today's usage of LLMs, we start asking in a lot of questions. So the context is building. It's not just you ask a question, you get an answer, and you're done with it. You ask a question, you get an answer, then you ask a follow-up question, and the way the LLM internally builds up that following question is that it takes the answer from the previous question and then it adds it to the next question being asked. So the context length keeps on increasing as you're asking multiple questions, follow-on questions. So for applications like that, the original positional encoding technique did not work. And actually, I'll go into more details at a little bit later part of the presentation. But these are the two fundamental challenges. Now comes the really cool innovation called Rotary Position Embedding or Rotary Position Encoding. This is a paper that was proposed in 2023. It's relatively new, less than 2 years ago. But pretty much since this paper was published, every commercial and every open weight LLM has actually shifted from using the positional embedding technique proposed in the original paper to using this. This is called ROPE, by the way, which stands for Rotary Position Encoding or Rotary Position Embedding. It provides three benefits. Number one, it actually encodes relative positional awareness. We'll see how that happens shortly. It is very compatible with self-attention, which is something that we'll study at a later point in this presentation today. But self-attention is pretty much the second landmark idea. Without that, there is no LLMs. So this technique actually is compatible with that. And that is one of the key reasons why it took off, like pretty much all LLMs use it today. And it generalizes well, which means that regardless of how long your training sequences are, even for very long inferences, it actually works well. And I'll actually explain to you how that happens. Other tutorials actually miss that, but I'll actually explain to you why it generalizes well. So let's try to understand ROPE. Let's start with intuition first. Let's say there are two sentences. Sentence one is dog show. Sentence two is show dog. Now, what I want to do in this slide is I want to give you an exposure to why positional awareness is important. Now, as a human, you obviously know that the first sentence, dog show, refers to an event. It's an event where dogs are shown by their owners, right? That's the dog show. The first sentence is an event. The second sentence, show dog, is not an event, but actually it's a dog that has been trimmed and made to look cute so that it can win an award. So the first one is an event, second one is a type of a dog, right? Now, what you want to do is mathematically you want to make sure that these two are different things. Now let's try to understand this. Let's say that the dimensions for these two words, let's say there are only two feature dimensions, animal and event. So the embedding for dog is 1.0, 0.2. Embedding for show is 0.1, 1.0. Now, if I were to put this on a graph, right? Again, two dimensions, I can plot it on a two-dimensional graph. So you can see that dog appears here, more of an animal, less of an event, and show appears here, more of an event, less of a dog. This is great. Now, the entire idea behind large language models and the transformer neural network architecture, which we'll study in subsequent slide, is this concept of self-attention, which means that every word in a sentence is measured or calculated to see how similar they are with other words in a sentence. In this case, each sentence has only two words. So let's try to see how similar are these two words to each other, right? The similarity between dog and show in the first sentence is you can measure this as a dot product between these two matrices. This is measuring the cosine angle between these two things. Remember cosine angle that I showed you a few slides behind? So if you do that, you see the first sentence, the score is 0.3. The similarity between dog and show is 0.3. Fine, that's good. Now the similarity between the second sentence, show and dog, is also the same because you're trying to measure the cosine angle between these two or the dot product between these two. Regardless of how you position it, the cosine angle remains the same, so they are the same. So if you zoom out a little bit from an LLM's point of view, dog show and show dog means the same thing, which is not the case. We know that show dog is an animal and dog show is referencing an event. So we have to have a way in which we can distinguish that these two sentences actually mean different things. Now, let's actually understand ROPE, how ROPE solves this thing. What ROPE says is, let's start with the first sentence, dog show. Again, the embeddings are the same. It says, how about I modify the original embedding matrix using the position information? But how do I do that? So let's focus on the first sentence, dog show. Dog is at position 1 and show is at position 2. So I'll take the first word, which is dog, and I'll figure out some angle, some theta. Forget about how that theta is determined. I'll show you that shortly. For the sake of an example, let's say in our case, the theta is, let's say 10 degrees. I'm going to now because dog is at position 1, I'm going to move this vector by 1 theta angle. Why 1? Because dog is at position 1 theta angles, I'll move this. Now, similarly, when I look at the next word, which is at position 2, I'll move this vector for show by 2 theta angles. The theta remains the same. Let's say it's 10 degrees. So the first word I'll move by 10 degrees angle because that's the first word. The second word I'll move by 2 times 10, which is 20 degrees because that's the second word. Now, if I do it this way, what I'm saying is I will rotate the embedding matrix for dog, right, by 1 theta angle or 10 degrees, and embedding matrix for show by 2 theta angles or 2 times 10, which is 20 degrees. So that's what I'm doing. How do you rotate a vector? Let's say the vector is represented as an xy in a two-dimensional space. How do you rotate? There is a formula in matrix calculation. It's a very simple formula. If you have an xy and you want to rotate it by an angle theta, then you multiply it with this what is called as a rotation matrix and it will give you the rotation. Very simple. You can reference back to any mathematics textbook on matrix manipulation. It will tell you that this is a standard formula. So if you apply the standard formula, what we have done is the embedding for dog is now moved by 10 degrees, right? 1 theta angle. And from 1.0 and 0.2, it becomes 0.95 and 0.37. And embedding for show is modified by moving it by 20 degrees because it's at position 2 times 10, 20 degrees. And it goes from 0.1, 1.0 to minus 0.24 and 0.97. Now let's measure using the modified embedding matrix. I get 0.125. Again, this is nothing but taking a dot product or taking a cosine similarity between dog and show. Now let's go to the next sentence, which is show dog. Now, what is my primary goal here? My primary goal is to figure out a technique in which I can show that these sentences actually mean different things, right? Now I'll apply the same technique here that I applied for the first sentence. Show is at position 1. So I move it by 1 theta angle. Let's say theta is 10 degrees. I move it by 1 10 degrees angle, which is 10 degrees I move it. Dog is at position 2. I move it by 2 theta angles. So I move it by 2 times 10, which is 20 degrees. So now the embeddings for E dog is rotate by 2 theta angles, the original dog embedding. The new embedding for show is rotate by 1 theta angles or rotate by 10 degrees, the original embedding for show. Now if you do that, the similarity between show and dog is 0.465. Now let's compare. Before applying any positional information or awareness, show dog and dog show are similar at 0.3 and 0.3 using simple math. After applying rope, I'm showing that dog show is 0.125 and show dog is 0.465. So now we see that just by putting the positional information, the calculations can distinguish between two sentences based on the positions in which the words appear. This is what the general idea is. This is how we have introduced positional information into the calculations. Now, again, this is not new. We have also studied something like this in the first episode, which is the original transformer had a different way. It did not rotate it by theta angle. It used this positional table using this standard table. It said for each position, I'm going to add this much things. So how is rope fundamentally different? Now let's get to the next level. Now that you have a general understanding of what rope is doing, now let's get to the next level. The next level is to get this relative importance. So let's say I have these sentences. The show dog was really cute. First sentence. Second sentence is the first place was awarded to the show dog. Third sentence is at the show there was a dog that was tall and big. And the fourth sentence is compared to other dogs at the show dog was tall and big. These are my different sentences. Now, let's try to measure again. Just focus on these two words. By the way, every word is scored against every other word. That's part of the whole self-attention in the transformer. We'll study that later. But let's just look at show and dog here. In this case, I rotate the first show by 1 theta angle and I rotate dog by 2 theta angles. Now the similarity is 0.465. Fine. Now let's get to the next one. First of all, what do you want to get? What you want to get is in this sentence, show and dog, absolute positions are different. In the first sentence, show starts at position 1 and dog starts at position 2. In the second sentence, show starts at position 7 and dog starts at position 8. However, their relative distance is the same. Remember that show and dog are next to each other in both the sentences, which means if I were to apply the same rotation technique and if I were to take a similarity, these scores should be the same. The scores between these two words in this sentence and these two words in this sentence should be the same. If I can do that, I know that I have encoded relative position information. Yes? Let's see that. So I take show, I rotate it by 7 degrees. Why 7 degrees? Because show is the 7th token. And I get this. I take dog, I rotate it by 8 degrees. And now I may take the similarity between show and dog. 0.65, exactly the same as this. So what have we established? What we have established is that rope allows us, just by using this rotation based on positions, it allows us to encode relative position information into the calculations. Now let's prove that by doing one more thing. Let's change the spacing between show and dog. If I do that, I move show by 2 theta angles and dog by 6 theta angles. Now, if I do show and dog, they are different. They're different from the first two ones. So this is very key because actually let me complete the next one. So in the next one, you see that there is show appears twice. I can measure the similarities between first show and dog, second show and dog. First show and dog, the value is similarity 0.749. Second show and dog, the value is 0.65, which is the same as the first two sentences because the relative ordering between show and dog is the same. Now, a few takeaways here. Adding positional information to change the embedding matrix is nothing new. It is there in the original transformer also. But what the relative positional encoding rope has done is that because it is using this angular movements based on position, it has also enabled us to keep the relative position information in this calculation. As you can see here, I can move the position of show and dog and the relative positions do not change, or their relative positions do not change in the calculations, correct? And this is super critical. This was not possible with the original matrix. If I were to take the original positional information and do the same calculation, each of these things will come up with a completely different result. So this is the beauty of using rope. All right, now this is all great for two feature dimensions. Notice that our original word embedding matrix is an S cross D matrix, right? S cross D. How does one rotate an S cross D matrix? For that, the rope paper on page 5 actually proposes a very interesting and a very simple solution. What you do is you take these different dimensions and you pair them. You say dimension 1 and dimension 2 is a pair, and for all the positions in dimension 1 and dimension 2, I'll rotate it by angle theta 1. Then I pick up the next two pairs, dimension 3 and dimension 4, I rotate it by theta 2. And so on. So dimension d minus 1 and d, I'll rotate it by theta d by 2. So what the paper proposes is that it can take an S cross D matrix and you can just create these pairs of dimensions. So you can get this x and y, and then you can apply the standard technique of using this rotation matrix. So theta 1 applied to this position, x and y. So for the same dimension, same angle theta 1, but 2 times because it's position 2. So same angle theta 1, 3 times because it's a position 3. Same angle theta 1 for 4 times because of position 4. Now you go to the next one. For these one, position 1. For these two dimensions, theta 2, 1 times theta 2 because position 1. 2 times theta 2 because position 2. 3 times theta 2 because position 3, and so on. That's what you do. So the calculation is pretty straightforward. I actually implemented this kind of to show you how it works. Let's actually start here. You take an embedding matrix, which is coming in the word embedding matrix E, which is S cross D. You go to each row. And then you define a position matrix. How does a position matrix looks for an entire row? It looks like this. It's nothing but this thing applied across all the dimensions. So if you look at this, this is theta 1 for the first position. This is theta 2 for the same position. See, the position is the same, but the dimensions have increased, right? And there is theta d by 2 for the same position. Then you got to and that is your rotation matrix. You multiply this with the original embedding matrix, you get the modified embedding matrix. Now you pick up the next row, which is the embeddings for the next token. You define the same matrix here, right? Which is the position now has become from 1 to 2, 2 times theta 1 here, 2 times theta 2 here, 2 times theta d by 2 here. So it's a very straightforward thing. So this is how rope works. So now you are here with this next step. So what we have done is, remember in the previous step, I showed you that you take the original word embedding and then you transform it with RMS now. Now you're further transforming it using rope, which gives it the positional encoding. At this point, you are good to go to perform the next landmark idea of the transformer neural network architecture, which is called self-attention. So let's understand that next. The core idea behind self-attention is to recognize that the same word could mean different things in the context in which it appears. Let's take a few examples to understand this idea. So let's start with this first sentence. I walked into Apple store eating an apple. The second sentence is sitting on a river bank, I was thinking about my bank account. And the third sentence is sitting on a river bank eating an apple, I checked my bank account balance using my Apple phone. Now, in these sentences, what you observe is that the meaning that you assign to the same word changes based on the context in which it is appearing. It means that it is dependent on the word surrounding it. In the first sentence, for example, the first occurrence of the word apple, is referring to a company, whereas a second occurrence is referring to a fruit. In the second sentence, the first appearance of the word bank refers to a landmass, whereas the second one refers to an organization, and so on. The key idea behind self-attention is to recognize that the word itself can carry different meanings in the context in which it appears. So the question was, how do we build this contextual awareness? As an example, for this sentence, I walked into Apple store eating an apple, and these are the different dimensions, dimension 1 through dimension 7, like the different feature dimensions of person, action, direction, brand, fruit, and so on. Now, the word embeddings are the same for the same word. So if you look at Apple, it has a score of 0.9 for brand and it has a score of 0.9 for fruit. And because the word Apple appears again, it will have the exact same word embedding, correct? Now, what we want to do with self-awareness is for the first occurrence of the word Apple, the value for the fruit dimension goes on significantly while it retains most of the value for the brand. Whereas in the second occurrence of the word Apple, the value for brand goes down significantly while it retains a significant portion of the fruit dimension value. So the general idea behind self-attention is you take the original word embedding matrix, which has already gone through the RMS normalization as well as positional awareness. You send it through what is called as a causal self-attention calculator. And what the causal self-attention calculator does is it will give you a transformed similar size S cross D size matrix, which is more context aware, which means that the individual feature values have either gone up or gone down based on the context in which each word appears. Now, one of the key things to understand here is that this causal self-attention is somewhat different than the self-attention that I taught you in the very first episode, because our training objective for a decoder-only transformer is to train it so that it can predict the next word. The technique called causal masking is used to calculate the self-attention scores. And I'll also show you that with a single line of code, you could achieve almost hundreds of millions of dollars of savings. So it's kind of very interesting. So let's dig a little deeper into what causal self-attention calculator is and what is that single line that can yield such a huge saving. Before we get into the actual implementation, let's intuitively understand this a little further. So let's say the training sample is I walked into Apple store eating an apple, and this is the original word embedding. And you would want to transform it from this original word embedding to this context aware word embedding. Now let's go step by step and see how this transformation happens. So let's pick up the very first word, which is I. What you do with I is I has, if you look at the original, it has a person dimension value of 1 because I references a person. There is no action associated with the word I. There is no direction. When the original word embedding is extracted, that's what it is. There is only person value that is assigned to I. Now, in this sentence, however, this person is doing something. So there's an action that this person is performing and they are directionally going into something, correct? And they are performing another action like eating, and they're eating some object, apple, and so on. So what you have to do is you have to trade the feature dimension values of this word with other words in this sentence. Like, for example, what you do is that this word I will give away a big chunk of its personness attribute to other words in this sentence. Okay. And it picks up from the other words certain bit of action. It picks up a certain bit of action from walked. It'll pick up a certain bit of action signal from eating. It will also pick up a certain bit of feature values from direction because this person I is walking into something, right? And it will also pick up certain amount of signal strength from brand, from this word apple, and a certain bit of signal strength from fruit, from the second occurrence of the word apple, and so on. And the net effect is that once this calculation is done, now this word I, originally it only carried the signal strength for person, but in the context in which it appears, which is the sentence, I walked into Apple store eating an apple, it has now picked up enough context so that I now carries enough context awareness. So you know who is moving, where are they moving in or are they moving out, into what, and doing what. Like for example, eating what? An apple. So you have modified each of these feature dimension from its original values, correct? Now, if you go into walked, you can do the similar thing. In the case of walked, there's a huge signal strength in the original word embedding for action. Now, what you'll do is that you trade some of that with other signal strengths from other dimensions. So in the end, what will happen is the net effect after this trade happens is the word walked is still a verb, it's still an action, but it is also tied more closely with the word stored, but it picks up a little bit of brand, a little bit of fruit, and all those things. Now let's go to, let's say, apple. An apple, if you look at it in the original, it has a huge signal strength for brand. It has a similarly huge signal strength for fruit. But here, this is the first occurrence of the word apple. And as a human, you understand that this apple refers to brand. And what we want to do with the self-attention calculator is we want to swing these feature dimensions in such a way that It does retain a major portion of its brand signal, but it gives away a significant portion of its fruit signal, because in this occurrence, the word apple does not mean fruit. So it has to give away its fruit signal significantly to other words. And it has to pick up signal strength from person, it has to pick up signal strength from action, signal strength from direction, and so on. Now you just keep going again and again to the next word and so on. Let's look at the next occurrence of the word apple. Same thing, the original word embeddings, the brand dimension was very high, the fruit dimension signal strength was very high. Now the trading happens as part of the self-attention calculator. Here, the second occurrence gives away a significant portion of its brand signal to other words, and it retains still a significant portion of its fruit signal. Now, why is it has gone from 0.9 to 0.75? Because it is trading with other words. By the way, these are just representative numbers. These are not really accurate numbers. I just use these numbers to show you the general idea. The numbers could be different, or the swings could be slightly more or less, or maybe similar also. But the idea to take away from here is the whole goal behind self-attention calculator is take the original word embedding matrix, look at each and every word, and then figure out how that word influences the other words in that sequence, and similarly how is that word influenced by the other words, and that influence happens through all the feature dimensions. So there is this really nice dance where the individual feature dimension scores are now adjusted, so that by the end of this self-attention calculator through the training process, you would now know what is the meaning of this word in the context in which it appears. And obviously, it does not happen with one training run. It happens with seeing literally thousands or millions of sentences or millions of appearance of these words in different contexts, and it'll build this thing. The goal for the self-attention calculator is you take the original word embedding matrix and then transform it into a context-aware embedding matrix, where each word's individual feature dimension scores are changed based on the context in which that word appears in that sentence, in the input sequence. Now, this is the intuitive understanding. Now, let's try to see how this is actually implemented. So, let's say that the original word embedding matrix I represented using this variable x. And what I want the self-attention calculator to do is create this attention modified embedding matrix. And let's say we call it y. So, how do you take a matrix x, which is an S cross D matrix, and convert it into y? Well, you can do that by defining a weight matrix. Let's say we call it w. And then if I multiply W with X, I can get Y, right? So if I present it this way, I take W, let's say I call it this gold matrix, which is a weight matrix. If I multiply W with X, I get Y. That is what I want to do. If I can reduce the problem down to this simple matrix multiplication, then I'm good to go. Correct? I already know X is the original word embedding matrix, which is S cross D. I know that I need to create Y, which is also going to be S cross D. So what should be the dimension of this gold W matrix? Well, it has to be S cross S. Because an S cross S matrix multiplied by an S cross D matrix will produce an S cross D. See, S cross S, S cross D, this S and S will cancel. So S cross D, correct? This S cross D. So that will give you an S cross D. So two things now, that this weight matrix is going to be the one that we have to figure out how to build. If we can figure it out, then we can perform this matrix multiplication and change the original word embedding to this context-aware word embedding matrix. So how do we do this? So let's figure out how you calculate these individual values of y. Y is calculated as what? Let's say y11, each cell. Y11 is calculated as this weight w11 times x11 plus w12 times x21 plus w13 times x31, and so on. You do this. Each cell is a multiplication of this row and this column. And I mean, similarly, other cells can also be calculated that way. This row versus that column. So this row versus that column. So this is a pretty straightforward matrix multiplication problem. Okay. Now, there is a certain property that you would like to give this weight matrix. So what is that property? So let's inspect the first cell here, y11. As I said, y11 is w11 times x11 plus w12 times x21 plus w13 times x31, and so on. Correct? Now let us say that w11 is 0.2, w12 is 0.1, w13 is 0.13. So these are different values of the weights, right? And through training, you start all with initially random values, but let's say it comes down to, after training, it goes down to this. Now, one way to look at these numbers is 0.2 is 20%, 0.01 is 1%, 0.13 is 13%, 0.43 is 43%, and so on, right? Now, let us say that you figure out a way in which you train it so that these weights, when you add them up, each row will become 100%. So this 20% plus 1% plus 13% plus 43% plus 3% plus 0% plus 11% plus 9% is 100%. So what does this tell you? Actually, what it tells you is, now you go back here, it tells you that in order to figure out the modified value of this feature dimension for the word I, will take 20% of the same feature dimension 1 from the word I will take 1% from the second word from the same feature, right? Dimension 1. I will take 13% signal strength from the third word's same dimension. I will take 43% of the signal strength from the same word's dimension 1 and 3% from the same features, the next word, which is store, and so on. So what it's showing you is that I'm borrowing a certain percentage of signal strength for the same dimension from the other words to construct my updated value for that feature. Now this we can repeat for every cell in Y. For every cell in Y, you apply the same thing. So now what we are doing here is what? We have gone from just not defining this W matrix, which is S cross S. We are also saying that if this weight matrix were to be trained in such a way that each row will become 100%, then we can get this really cool, nice feature that you're taking a certain portion of the signal strength for a feature from all the words to determine the modified value of that feature for each word. And you can do that across every word, across all features for every word. So what we have come up so far with is, you already have this word embedding matrix X. In order to produce the context aware word embedding matrix Y, I just need to define a weight matrix, which is S cross S, all randomly initialized to some random values, and I have to train it in such a way that each row of this matrix becomes 100% when you add them up. That is the property of this weight matrix. With this basic understanding, now let's dive into what was originally proposed in the paper. So in the original paper on page 4, the formula for calculating self-attention is shown like this. Now, just with every other episode of my deep learning web series, our idea is to actually intuitively understand these formulas, not just take them for how they are presented in the paper, but try to understand why it is actually presented this way. So let's try to understand that. And again, self-attention is the second landmark idea of the transformer paper. In fact, there are only two landmark ideas in the whole transformer paper. First one is positional encoding, and the second one is self-attention. Everything else is brilliant engineering work, but the two novel ideas are these two. So let's see how this is done. Okay, so our idea here is, at this point, you're going to get the original word embedding matrix. And once it goes through the self-attention calculator, it should produce this context-aware embedding matrix. Now we need to fill up this portion. So I implemented the self-attention calculator using NumPy, so that it's a pretty straightforward, easy implementation to follow. And let's understand this step by step. So let's start at the bottom here. So let's say our training sample is, I walked into Apple store eating an apple. I already told you that we add the special start of sequence token to it. So you add that and you convert these tokens into its word embeddings, right? Which is the numeric format of that, which happens here. So this is my word embedding matrix. Okay. Now what I want to do is that I want to send it through the self-attention calculator here, which is this block that we'll fill up shortly, so that it produces this attention enhanced context aware, same as cross D matrix. So how does this happen? All right. So the first thing is, we take this embedding matrix and we make 3 copies of this embedding matrix. And the way we make these 3 copies is, first we define 3 trainable weight matrices. First one we call as WQ, the second we call as WK, and the third one we call as WV. Now the size of these weight matrices is D cross D, which D is what? The total number of feature dimension. Now with this, we'll make 3 copies. The first copy we'll call as query. How is this copy made? Well, it's pretty straightforward. You take this incoming embedding matrix X, you multiply it with WQ to get query matrix. You take the same embedding matrix X, you multiply WK and to get the key matrix. And you take the same embedding matrix X and you multiply it with trainable WV matrix, you get the value copy. So query copy, key copy, and value copy. Now we have made a copy. So far in this copy, there is no positional awareness. If you remember the picture here, you just get word embeddings, and all we have done is you have done the RMS norm. The rope happens after you're done this. The rope is providing positional embedding information that happens after RMS norm, right? So what we have to do is we have to enhance this copies, query copy and key copy, with positional awareness. Now, one obvious question comes up is why are we not doing the same for the value copy? I'll explain that later. In the modern transformer, the query copy and the key copy are the only ones to which we apply the rotation. The way you make this copy is you rotate them by these different angles. We already studied rope, right? So what you get is your QR, which is the rotated matrix for query copy, and KR, which is the rotated key copy. So this is pretty straightforward. Now let's just step out a little bit and remember that when I was teaching you rope earlier, I told you that in addition to providing relative position information, rope also generalizes very well, and it makes it possible to build the modern day applications like ChatGPT, which was harder to do with the original positional encoding technique that was proposed in the attention paper. Let's try to understand why that is the case. So in the original transformer paper, before rope, the way positional encoding information was added was that you took the word embeddings, which happens here, right, which is word embeddings for these tokens, and then to that you added this absolute positional embeddings, right, which is a table based on the sine and cosine and so on. So what goes into the transformer is the summation or the combination of this word embeddings plus the positional embeddings. This now is your x, right? Now what you do is that you make this query, key and value copy by multiplying this x, which is an addition of both the embedding plus the positional encoding with their corresponding weight matrices WQ, WK, and WV. And then you calculate the attention using the self-attention formula. So in code, it looks like this. Original is word embedding E, positional is P, the input X becomes E plus P, and then you make this copy where you take this X and then you multiply it with the weight matrix. Now, what has happened after rope, which is pretty much every modern large language model and transformer uses this technique, is it changes to something like this. You take the original word embeddings, just like you do with the original transformer. That's what happens here. And then before you add positional information, you make the copies by multiplying it with the weight. So you make the query copy by taking just the word embeddings, and then you multiply it with WQ. And after that, you rotate the query and key copy. So why does making this small change makes possible the modern day LLM applications like ChatGPT, where the context length is like 128K, where people just don't ask a small question and expect a very short answer. People ask a question, they get an answer, they ask a follow-up question. In order to feed that follow-up question, the answer from the question is also embedded as a context for the second question and so on. You build over that. So over time, you see that the context window gets larger and larger in any modern LLM. So what happened is in the original transformer, because the positional embedding happens before you make this query copy, key copy, this weight matrix starts to learn this positional embedding values also, which is not bad, it's fine. But now think about the following case. Let us say that during training, the maximum sequence that it sees is, let's say 100 tokens. So up to 100 tokens, this weight matrix, this WQ and WK are learning how to handle sequence lengths that are up to 100. Let's say even 200. But what happens during inference is that because your context window is increasing or context length is increasing with every follow-up question you're asking, you would see a context length or the input sequence length to be far more than what you had given during training. Let's say you keep on asking a lot of follow-up questions, which is a very common thing that we do with the modern day ChatGPT. So you would see that your context length will start increasing from hundreds to thousands to 10,000s. Right now, the ChatGPT 4 has 128,000 context length. So you can pack it with a lot of context. However, in the original transformer, this weight matrix is only learned because it is applied right over the combination of the positional encoding plus word embeddings. It has only learned whatever it has seen during training. And during training, unless you are providing very large input sequence, it would not have seen that length, right? So which means that you actually have to construct things that are very long in terms of context during training, which is not always feasible. So what the rope technique does is that it says, I'm not going to make this weight matrix learn anything about position embeddings. That's why I'm going to take it out and put it after this query copy, key copy. And I'm not learning anything about the positions. In the original transformer, let's say that your training was for up to 100 positions. It can learn everything up to that. But as your context window during inference goes to tens and thousands, it does not learn, so it's trying to extrapolate. So the quality of your responses is going to go down across very long context. With rope, what has happened is that because the weights are not learning anything about the positions, there is no impact on the quality of the response, even if the context length is very large. Now, if this were not implemented, we would not be able to see the modern day large language models where we have these multi-turn conversations with LLMs and they are able to answer while retaining all this context across very long lengths. So, in addition to providing relative position information, which was lacking in the original Transformers positional embedding technique, rope also has a superb advantage that you could handle longer context during inference, even if your training has not seen text with that long a context. So this is brilliant. All right, let's go back to the slide here. So what we are seeing here is that once the query key and value copies are made, you rotate the query copy and the key copy. Rotated by what? Those angles that I talked about earlier, which gives it the positional awareness. Now, obvious question, why are you not doing it with value? Because in the original transformer, even the value copy had the positional embeddings added. Now, the reason that we don't need to do that in rope is because, as you will see through the self-attention calculation, the positional awareness is only needed when you're comparing how each word is related to the other word in that sequence. Rotating the value matrix, it adds no real impact to the final calculation. All right, now that you have QR, KR, and V, what do you do with it? The first thing you want to do is how similar is each word to the other. So that is what happens here. So you're creating an attention score. So far, if you notice, each of these matrices is still S cross D. Remember that our goal matrix that you finally want to get to is an S cross S matrix. So we need to first figure out how to start off with that S cross S matrix. That happens with the attention score matrix. So let's try to understand this a little better. So you take your rotated query matrix, which is here. You take your rotated key matrix, which is here. Now, what do you want to do? What you want to do is I want to see how similar is I compared to all the other words in this sequence. How similar is walked compared to all other words in this sequence and so on, right? Why do I need that? The reason I need that is because I need to now start to trade the feature dimension signals from one word to the other. For that, I need to know the similarity or dissimilarity or unrelatedness of each word to the other in this context and so on. So you have your S cross D size matrix, which is the query matrix, and you have the S cross D for key. You cannot multiply S cross D with S cross D. So what do? You transpose it. When you transpose it, you get your S cross D and D cross S. When you multiply that, you get your S cross S matrix. Brilliant. Now we're getting somewhere. Because remember, we wanted this golden W matrix, which has to be shaped as S cross S. So you have your S cross S here. And this is a beautiful matrix because now you can say, across each of the rows and across each of the columns, I can figure out the similarity scores. The way you figure out the similarity scores is taking a dot product. The dot product is, for example, if you want to figure out S1, you take the dot product and then you say S1 here is Q11 times K11 plus Q12 times K12 and Q13 times K13 and so on. So this is going to be my attention score. So this matrix that I get, S cross S, is going to be my attention score matrix. What is the size of this matrix? S cross S, right? S cross D times D cross S is S cross S. Now, there is something that's very interesting that's happening here. Now, if you notice, each of these values, each cell S11 is adding up for each feature, for each word, it's adding up, right? So the total number of additions that you do here is proportional to the total number of dimensions. So I had 8 dimensions here. So I have 8 additions here. If I have 1,000 dimensions, I'll have 1,000 additions here. A modern day large language model, let's say GPT-4 or something, has, I think, 16,000 dimensions. So you have 16,000 additions here. So which means that this number starts to keep on growing bigger and bigger as the number of dimensions is increasing. If you size your transformer to have like 16,000, it's a very large number. And in general, deep learning does not do well with large numbers because large numbers can swing calculations in very significant ways, which you don't want. So you have to normalize these large values. You scale it down so that even if the total number of dimensions is large, these individual values in each cell does not explode. The way you do that is that you take your attention scores that you see here and dividing it by the square root of the total number of dimensions. Now, the central limit theorem suggests that when you add up D independent random numbers, the results typically has a size or spread that grows with the square root of D. not with d, but the square root of d. That is why to scale these numbers, we divided by the square root of d. Again, d is the total number of dimensions. All right, so that's what happens in this line. Attention scores are now scaled by dividing by the square root of the dimension. So now what we have is scaled attention score. Again, the size of the matrix is still S by S. It is just that the individual cells are now scaled. Now let's get to the next one. I'm going to skip this mask for a second because I think I need to spend some more time to explain what causal masking is. It's a very interesting thing, but let's skip that and let's go to the next one. Now, what you want to get is this attention weights. These attention weights. Now, this is the gold matrix that we said, the original W matrix that we want to get, whose property is that every row adds up to 100, correct? So how do you get that? So that you get every row adds up to 100? Well, you apply the softmax function. You apply the softmax function to the scaled attention scores. So you get this W attention matrix, which has this property. Now you multiply this W attention matrix with the value copy. So what you have done is that you have taken X, which is the original word embedding matrix. You run it through the self-attention calculator, and what you got is the context-aware self-attention matrix. Now we skip this very important line called causal masking. So let's understand that next. For that, let's go back to this diagram here. And what I told you is that the training objective for a decoder only large language model is you want to train it so that given a certain set of previous tokens, it will predict the next token. But so far, whatever I've shown you is that I've taken all the words that are there in the training input and then passed it to the transformer. And if you just go back to this picture here, as you can see, right, I compare all the words with every other word in that input to figure out how similar and dissimilar they are. But that's not what we want. What we want is I'm just going to give you, let's say, a startup sequence, SOS. I'm not going to give you any words after that, and I want you to predict I. Similarly, if I give you SOS and I want you to predict walked. And if I give you SOS, I and walked, I want you to predict into. So what we want to mimic is while I'm giving you all the words in the input, I don't want you to actually see the words that come after the current slot at which I want you to make the prediction. So in another way, so I'm going to give you SOS, I want you to predict I. If I give you SOS and I, you predict walked. If I give you SOS, I walked, you predict into, and so on. So I have to make sure that the transformer does not see or peek into the future. Future is what? So let's say it's trying to predict the word at this slot. Let's say it's slot 3. The future is the words that come after slot 3, right? Which are all these words, Apple Store and all that. So it cannot, and while I'm giving it as an input, I do not want it to peek into that and start to do the attention scores based on future words. And it has to do that for every slot. So in this slot, let's say slot 2, where is this? Slot 2, it cannot peek into the words that come after that. In slot 3, it cannot peek into the words that come after it. In slot 4, it cannot peek into the words that come after it. Now, one way to do that is to take an input sequence and then do the training this way. Let's say the input sequence is n tokens, then I pass the first token, get the prediction for the token that comes after that, then pass the first 2 tokens, get the prediction for the next token, and so on. I do that. Now, that is going to be terribly slow. Okay, now how slow is that? Let's try to understand that. So if there are t tokens in a sequence, you call the training loop t times. For each sequence, you're calling it t times, right? Now, actually, OpenAI published this number to say what is the average number of tokens it sees per sentence in the standard training set that you download from the internet. And it observed that there are about every sentence has an average of 17 tokens, which means that your training run happens 17 times per sequence that you insert. Let's just put this in perspective. So let's say you take Llama 3, which has 70 billion parameters. Now, the number of training tokens that Llama 3 is trained on is 2 trillion tokens. It has about 80 billion sentences. 80 billion training sentences in its training data set. And they train on 2000 GPUs. It took them about 60 days to do the training. It costed about $20 million. GPT-4, on the other hand, is a much larger model. It's a model that has 1.7 trillion parameters. The training data set has about 760 billion sentences, right, on which it was trained. It was trained on 25,000 GPUs. It took 90 days to do this training. Again, more number of GPUs, but again, a huge number of training samples, as well as massive increase in the training parameters as well. And it costed OpenAI $100 million to do the pre-training for GPT-4. Had they done this by giving it one token at a time, or rather, had they done it by making it predict just one token, by doing this strategy, right? Take the incoming sentence and break it into first word, predict the next token, first 2 words, predict the next token, first 3 words, predict the next token, and all that. You would have a 17 times explosion, right, in the cost and the time. Why 17? Because on an average, there are 17 tokens per sentence. Which means that if you were to train it like this, although it's very intuitive, Llama 3 would have taken 2.8 years to train, not 60 days, and it would have costed $340 million, not 20 million. Similarly, GPT-4 would have taken 4.2 years, not 90 days to pre-train, and it would have costed the OpenAI $1.7 billion, not 100 million. So clearly, while the strategy is correct, it is a very poor strategy when it comes to practical value. So you need to have another technique, and that technique is I'm going to pass the entire sentence as is, and I want to make this transformer not peek into at any given stage. If it's trying to predict a token at a particular slot, at a particular position, it will make that prediction without peeking into the tokens that come after that position. That's what you want to do. And that is what causal masking does. So how causal masking is implemented is, let's say your S cross S matrix looks like this, all words. So rows and columns are the words. Now what you want to do is, you want to make this prediction. For each position, you want to predict I. And for position 1, you want to predict walked and so on, correct? All right. What you want to do is that you want to mask these slots, these cells, which means that I now have mimicked this. If I just give you SOS, I predict I, because I have masked everything that comes after SOS. For position 1, I give you SOS and I make the transformer predict for that slot the next token to be walked, because I have masked everything after that. I give it SOS, I and walk. I have masked everything after those, so I can predict into. So now we're getting somewhere. So where did we see this S cross S matrix before? I'm showing you as an intuition here, but where did we see this S cross S matrix before? Well, we saw it here. The attention weight matrix. This is an S cross S matrix, correct? So clearly we have to do something here. Now we have a clue. We know that we have to do something here, so that we apply this masking technique, so that when you're doing this calculation, it does not peek into the future, right? How do you do that? So you take this weight matrix, this golden S cross S attention weight matrix, and you have to mask all of this out. When you mask all of this out, if you notice, the original one is every row adds up to 100%, right? Which is what you want. And when you mask it also, you want it to add up to 100%, but which means that this weight itself should be 100%. These two weights should be 100%. These three weights should be 100%, and so on. Now, how do you get that? How do you make this happen? So the paper, Attention is All You Need paper, proposed this technique of using this mask, what they call as causal mask. And it's a brilliant idea, which saves us from doing this training run by passing it one token at a time. And the way it works is, you take your scaled attention scores, which is this one here, the scaled attention scores. You into this here, and then you define what is called as a causal mask. And a causal mask is what? Causal mask is, you put zeros here, and then you put minus infinity on the upper triangle of this matrix. So actually you can see that here. You see that np dot this triu means define a triangle matrix where the upper is made up of minus infinity. So notice that all of this, the lower triangle is all zeros, the upper triangle is all negative infinity. So what does this do? So how does this help us get to that thing? Well, think about it this way. When I add these two matrices, the original scaled attention scores, then I added with this causal mask, which is nothing but the lower triangle is all zeros, upper triangle is all negative infinity. What do you get? You get the S11 and all that will be the same. The lower triangle will be exactly the same as the attention scores. But the upper triangle, because you're adding minus infinity to some number, it is minus infinity. So what you have done is, just by adding this causal mask, you've transformed this scaled attention score to masked and scaled attention score, right? So you've masked out this upper triangle. So what? So what if you have masked it out by putting negative infinity? Well, if you run this through a softmax function, right, which is what happens here, the softmax function. If you run it through a softmax, what do you think happens? Remember that a softmax turns everything into a probability distribution. So each row has to be 100%, right? And because the numbers are too small, one of the properties of softmax is that if the values are too small, it brings it down all the way to zero, so that it keeps the other values that are not small, right? So all these things that are negative infinity, because you're applying the softmax, become zero, and the entire weightage now shifts to the non-zero values. So all these cells in the lower triangle matrix start to have their values all swing towards 100% when you add them up, and everything in the top triangle matrix becomes zero. Now boom, we have that. Whatever we wanted in terms of causal masking has happened just by adding this one line. Now this single line of code is very elegant, very simple. It saved us from doing the training runs by feeding it one token at a time, by feeding the entire sentence or entire sequence of text strings into the input context window in one shot. I think this is a brilliant idea. Just by using one line of code and some very, very clever tricks and exploiting the property of softmax, we are able to accomplish this without really going through feeding each word at a time while doing training. So that sums up our mass causal self-attention calculation. So if you map it back to what is proposed in the paper, you see that you make this query key and value copy, you do a matrix multiplication of the query and the transpose of the key, and with the enhancement with rope, you take the query and key copy and then you also rotate them so that you get them positional awareness. And then you scale them by dividing by the square root of the total number of dimensions. Then you apply masking and then you apply softmax. And then you take the final output of that and multiply it with the value copy. And now you have this beautiful attention weighted context aware matrix. So we originally started with the word embedding matrix here. You send it through a transformation with RMS norm where you normalize it. You gave it positional embedding, which is this pink matrix. So you gave that and then you run it through the causal self-attention, and now you're transformed it so that this embedding matrix now is context aware. If you look at the decoder-only transformer architecture, you see that this block here is called multi-head attention, not self-attention. So what is multi-head attention? So if you zoom out this box here, you see that you have the S cross D matrix that goes into the self-attention calculator and then comes out the context aware S cross D embedding matrix. Now, in multi-head attention, what you do is you take the input embedding and instead of passing it through just one self-attention head, you slice the input word embedding into multiple slices, and each slice is picked up by its own self-attention module. And then all of those self-attention modules calculate the self-attention across only a subset of the dimensions. And then once they are done with the self-attention calculations across just those subset dimensions, they are all joined together again. And then you get the final context-aware embedding matrix. So the primary benefit of multi-head attention is that it improves performance almost 2 to 4x, and it also improves hardware efficiency. But I actually don't want to spend a lot of time going into all the details as to why it improves the performance or improves hardware efficiency, because I have covered this exhaustively in episode 1 of season 3, and in the interest of time, to make this video not become too long, I will not repeat it again over here. But one thing that I will call out is many tutorials out there incorrectly state that because of multi-heads, each head specializes in a certain aspect of language. Actually, that is not true. And again, I explained the details of all of those things in episode 1 of season 3. I would highly encourage you to go back and look at that section of the presentation again. The next part of the decoder only architecture is residual connections. So residual connections are, I'm showing this with an animation here. So these are, think about it as shortcut paths where you add the input that goes into one block is also added back to its output so that you can have a very smooth flow of information through the transformer neural network architecture. And the primary benefit for that is that it helps stabilize training. Again, I actually go through a lot of these details in episode 1, season 3. In the interest of keeping this episode small, I will not repeat it again over here. So I would highly encourage you to go back and review that if you're still interested in knowing what residual connections do in the transformer. And now that we have seen the transformations that have happened so far to our input embedding matrix, after the self-attention, you do the residual connection and also do RMS normalization again. And then we move to the next step of the transformation, which is called as feed-forward network or feed-forward layer. Now, what is the purpose of this feed-forward layer? Why do we need it? Well, let's look at these sentences. I walked into Apple store eating an apple. Let's look at another sentence. I entered an Apple store chomping on an apple. Let's look at a third sentence. Taking a bite out of an apple, I stepped into an Apple store. Now, to a human, walked into, entered a, stepped into, more or less mean the same thing. Now, self-attention, of course, has swung the feature dimension values up and down based on the occurrence and the position of the words and the context in which they appear and all that. But we also want to go one step further. What we want to do is that we want to handle this case where different sentences can mean the same thing. And the way you would do that is when you expose the LLM while training to different sentence constructions, it learns that walked into Apple store and entered an Apple store mean the same thing. Again, purely based on the appearance of the words or the occurrence of these words. For example, I walked into Apple Store, it sees in one training sample, and it also sees I entered an Apple Store. It says, oh, what? I think they're the same thing. After walked into, Apple Store can appear, or before Apple Store, walked into can appear. Or similarly, after entered an Apple Store can appear, or before Apple Store entered an can appear. So, which means that walked into and entered an, setting the same context between the preceding word I and Apple Store. So that's how it learns. But we need something to make this happen, and it cannot happen in the causal self-attention module, right? So how do we do that? Well, the way we do that is that we need more weights so that this is learned. Obviously, you just cannot randomly add more weights. So what is a meaningful way in which you can add those weights? So once you've gone through the multi-head self-attention, what we want to do is that we want to inspect, right, each of these words at a much higher dimension. As an analogy, think about it like this. You have a magnifying glass, and originally you had d dimensions here. You want to magnify it further and start to look at each of these dimensions at a much more nuanced way. How do you do that? Well, you can use a feed-forward neural network. In a feed-forward neural network, you can define it as a two-layered feed-forward neural network where you project this S cross D matrix so that these D dimensions in the first layer, you kind of project it to a much larger, much wider dimension space. How wide? 4 times the dimensions is 4D times. You project it to that 4D dimension space. So an analogy is that you're taking a magnifying glass and zooming in 4 times to now try to understand the relationship between words and different features. Now, if you do that, you get an S cross D matrix multiplied by 4. D cross 4D will give you S cross 4D. You don't want that because you want to preserve your S cross D matrix size as you're moving up the transformer chain or the stack of components. So which means that in the second layer of your feed forward network, you have to project it down back from 4 cross D back to D. So zoomed in, looked at it, you've trained your weight, now zoom back out so that you get the original size matrix. So that's what the feed forward neural network does. It's something like this. Your X attention, which is the what comes out of the self attention module, is S cross D matrix. You multiply it with the first layer, which is D cross 4D, which will give you a S cross 4D size matrix. So you're zooming in 4 times, and then you project it back from S cross 4D down to S cross D using this 4D cross. You're zooming out from 4D to D. So in a feed-forward neural network, when you're going from one layer to the other, you need to have an activation function. Yes. So that activation function we'll study next, but just kind of zoom out a little bit and try to understand what has happened here. In the self-attention calculation, what we have done is that S cross D matrix, we adjusted all the weights so that it is context aware. What we have done here is that we have not changed the weight values of S cross D. Instead, we have defined more weights over here in the feed forward neural network, and we are training those weights so that over time we can understand that I walked into Apple Store, I entered an Apple Store, I stepped into an Apple Store, it means the same thing. That is what a feed-forward neural network does. So in the more modern incarnation, which came out in 2024, this layer is replaced with something called mixture of experts. We will go into those details in another episode, but the purpose of this part of the transformer block is to get a better nuanced understanding of language. Now let's look at this activation function. Remember that in any feed-forward neural network, you have to have an activation function that will transmit the values from one layer, which is this layer, to the next layer. And why do you need an activation function? Because you have to add non-linearity. I've actually explained activation function with a lot of examples, both in episode 1 as well as episode 3 of season 1. I go into a lot of details and explain what it does, why you need it, what will happen if you don't have it, and all that. I'll not go into more details, but if you want to know more about what an activation function does, you can go back and refer to episode 1 and episode 3 of season 1. Anyway, so far the activation function of choice has always been what is called as ReLU, which is the rectified linear unit. Now, rectified linear unit is a very straightforward activation function. All it says is any signal that's coming from this layer, if that signal strength is negative, I'm going to drop it completely. And if it is non-negative, I'll pass it as is. So if you look at, just focus on the red graph here. In the red graph, which is value, which means that any value of input x that I'm passing, if it is negative, I'll always make it 0. I will not let negative values go from one layer to the next layer. And if it is a non-negative value, 0 or positive, I'm going to let it go through as is. That's what a rectified linear unit is. ReLU, it might seem very trivial and simple, but it has become the most popular activation function in all of deep learning. However, intuitively, you know that while ReLU does this non-linearity that is needed when you're defining a feed-forward neural network, I mean, the fact that it drops all negative values It doesn't sit right. I mean, obviously, yeah, I understand that negative values maybe not carrying much information, but you do want to pass some negative values, right? So there's been a lot of work around that where you have leaky ReLU and this and that where you pass some of those things. So the state of the art right now is what is called as SwiGLU. SwiGLU is the swish activation function with gated linear units. What I mean, I think the easiest way to understand this is you define another set of weight matrices within the activation functions themselves. So you're learning something there where you gate how much information goes in from the first layer to the other layer. And the goal here is what you see in this purple picture here. In the purple picture, you see that, yeah, some of the negative values it will let it go through, and even the positive values, it kind of gives it some curvature. So it looks like ReLU, but it does pass some of the negative values into the next layer. Now, this is a idea that was proposed in 2020 by one of the original inventors of the transformer neural network, the attention paper, Noam Shazir. In this paper called GLU Variance Improved Transformer, just by making the small change, they found out that the transformer was performing much better. And at this scale, when you're talking about billions of parameters across all the different layers of the transformer, it's very hard to kind of comprehend why this small change has a big significant impact. And in fact, in this paper, it's kind of interesting that the very last line, the concluding line of this paper, the author writes this. He says, "We offer no explanation as to why these architectures seem to work. We attribute their success as all else to divine benevolence." Now, this is interesting because he's right. I mean, you could have some intuitive feel of why it is working, but if you were to mathematically prove why this is working at the scale at which you're talking about, billions of or trillions of parameters, it's really hard to do that. Sometimes empirical observations, just running experiments, and you see that you're getting better results, you stick to that. Anyway, so all modern transformers have switched to using SwiGLU as their activation function for the feed-forward neural network layer. Alright. Now we have gone past the feed-forward neural network, and now we have your S cross D matrix, and we also have trained other weights in this feed-forward neural network. Let's get to the next topic here, which is called stacking. What is the general idea behind stacking? So language is complicated and it requires multiple passes for us to build relationship among words. For example, if I give you this sentence, wisdom is chasing you, but you are faster. Now, if I were to give this to a middle schooler whose exposure to sentences and phrasing is limited, they might actually interpret this in a very literal way. What's so funny about it, right? It's pretty straightforward, literal interpretation. But you give this to someone who has gone through high school or undergraduate degree, who has been exposed to more sentences, they will understand the wit and the humor in the sentence. They don't just go with the literal meaning because they have studied so many other sentences. They will try to form actually what is being conveyed here is very funny and humorous. So, how do you make the machine learn this? Well, the way you make the machine learn this is to make it mimic what humans do. You make the machine see the same things again and again and again and again by trying to dissect, analyze the same inputs in multiple ways. So stacking is that technique. So what you do with stacking is you take this decoder block and it has a certain set of weights and you pass the input. Now the output of the decoder block you pass to another decoder block, the same architecture but its own set of weights. The output of that you pass to the next decoder block. The output of that you pass to the next decoder block, and so on till you go to the final output layer of the transformer. So each of these decoder blocks, the architecture is the same, only that each one has its own set of weights. So what it means is that it's almost like you're looking at the same text, analyzing it once, then modifying or transforming the input, passing the transformed input to the next block, which is again dissecting, analyzing it again, and so on. So what they found out is that doing this actually has had a tremendous benefit in terms of better understanding of language. So much so that the original transformer only had 6 blocks. Even the original attention paper, they actually understood the importance of having these multiple blocks, but they defined it at 6. But when it came to Llama and DeepSeek and GPT, you started to see hundreds of blocks. The same decoder block repeated 100 times. It adds a lot of computation, it adds a lot of training time, but it improves the quality of interpretation of words and their meanings. So Clay Bauer, who was part of the Google DeepMind team, actually explains this in the following way. He says that when they started to see the amazing things that generative AI could do with the decoder-only transformers. I mean, they of course they were really impressed with the fact that it could generate a text given a set of sequence of tokens before it. But what blew their mind is when they asked this question: "Please explain the 2008 financial crisis using movie references." And it blew their mind that what the LLM at that time could produce was something like this. It said, so the 2008 financial crisis was like the movie Inception, except instead of dreams within dreams, it was debt within debt. Now, this is those who actually understand the CDO within CDO and the whole 2008 financial crisis will be able to appreciate how profound this is. That the language model, just by looking at sentences, could actually build a level of understanding of different concepts at this level that it could take something what it has learned from maybe while trying to scan the script of the movie Inception and what it has learned from looking at all the documents related to financial crisis 2000 financial crisis. It's able to make these connections, and all of that is because of all these layers that we have in the transformer architecture. Okay, I think it's phenomenal that a machine can produce an answer like this, right? Now think about it this way. Let's say I had not shown you this answer, and if I would ask you this question, please explain the 2008 financial crisis using movie references. Perhaps the first thing that will occur to us is maybe I'll explain it using the movie Big Short or Margin Call or something else. But the fact that it could actually make this analogy and explain it using the movie Inception, I think it tells you how powerful this transformer neural network architecture is. Right. With that, let's go to the final thing, which is the output layer of our transformer. So just a quick summary, we have the original embedding X here, which is S cross D. It goes through the mass attention and it produces this green matrix, which is the attention enhanced context aware same matrix S cross D. And by the way, the weights in the attention layers are WQ, WQ, WV times the number of heads plus the output for coalescing all the outputs from individual heads. Now this matrix goes to the feed-forward neural network. The feed-forward neural network has again multiple weights, and then what comes out is that XFFN. You get this. Now you pass that through multiple decoder blocks, which is the stacking that we told you earlier. And then from there, so far what do you have? You have just S cross D. What you really want is for each of these slots, you want it to predict. For example, if SOS, I want you to predict I. If it is SOS and I want you to predict walked. SOS and walked, I want you to predict into and so on. Which means that you need to have what? You need to have a matrix that is sized as S cross V. SY, there are S is the total number of slots or number of tokens that is there in your input, right? You need that. But for each of those slots, each of those positions, you have to predict among all the vocabulary words that you have. Let's say you have V vocabulary words. You have to figure out which of these vocabulary words actually fits in this slot, which of the vocabulary words will fit into this slot, which of the vocabulary words will fit into this slot, and so on. So how do you go from an S cross D to an S cross V matrix? Well, you use a projection layer, which is nothing but one neural network that with a weight matrix. So S cross D times D cross V will give you an S cross V. So this weight matrix is a D cross V weight matrix that will allow us to go from S cross D to S cross V. Well, once you have this, you apply softmax, and once you apply softmax, it will just pick one of these slots and say, I think for this position, I think the word that appears in this slot is the most appropriate one. For this position, this is the word that is the most appropriate one, and so on. Initially, of course, and from there, of course, you make your prediction. Now, you compare that prediction with your ground truth value, and you calculate the loss using cross entropy loss function. Why cross entropy loss? Because you're using softmax as your output function. Now, initially, when we start off, all these weights are random, which means that your predictions are going to be completely wrong, right? Which is fine. Because as you are running this through again and again through multiple billions of training samples, it will get better and better and better. So these weights will swing themselves in such a way that the predictions will be equivalent to what you see in the ground truth value, which means that your loss is very, very low. But once you have this loss, you propagate that loss. So if you look at it, the total number of weights can be modeled like this. You have n number of blocks, and each block has these many number of weights plus the final projection weights and so on. And I show you in this table here for different types of large language models, what are the total number of parameters. And when you see a total number of parameters, I mean, you hear this thing, Llama 2 has 70 billion parameters. This is how it's calculated actually. If you just take these numbers, plug them in here, you will get these numbers. All right. So how big is the training data set so that decoder-only large language models can actually understand language? Well, the training sets are very large. If you look at some of the popular open training data sets, you actually look at the size here. Even for a small model, which has the 1 to 13 billion parameters, the training data set, which is downloaded from the internet, is about 825 gigabytes, about 400 billion tokens. If you look at the Falcon data set, it has multiple terabytes, about 3.5 terabytes of raw data and 3.5 trillion tokens. There's the common internet crawl data, and these are used for training large models like 40 billion to 180 billion parameter models, and so on. So they are all very large. If you notice, even the smallest of language models sees triple-digit billion tokens, and the typical large language models see trillions of tokens. By comparison, an average human sees about 1 billion token in their entire lifetime. Like between the, let's say, the first years from when they start to learn language till 80 years of age, they see about 1 billion tokens in their entire life. Not unique tokens, tokens or words in different sentences. A voracious reader keeps on reading more and more books, they might go to 2 billion tokens. An entire human in 80 years of their lifetime. A small large language model is exposed to about 400 billion tokens. A model like Llama 70 billion or even GPT and all that, they're exposed to trillions of tokens. Now you can understand that just by getting exposure to massive amounts, we're talking about like tens and thousands of orders more huge than what humans are exposed to. You can actually, with a very smart architecture like the transformer, you can make the machine learn language. And when you say learn language, these are the things that it learns: how words flow together, how context shapes meaning, how connections can be formed across sentences, what are the different syntactic and semantic rules that govern languages, and it also picks up general knowledge, right? Now, this completes our understanding of how you train a large language model. So, at this stage, we are done with step one, which is pre-training. The large language model went from untrained transformer to a pre-trained LLM, which has acquired all this knowledge about language. Now, what I will do is I'll go a little out of order, and then we will study step three next, which is taking a trained large language model and inferring from it, which is if you ask it a question, see how it produces a response. And after step three, I'll come back and show you step two. And the reason I'm doing this a little out of order is because I want you to get a complete picture of training followed by how the responses are produced. The fine tuning step, which is the middle step, is a way in which you can bring alignment of the LLM's responses to human preferences. It's a very important step, but I think going from training to how responses are generated from a trained large language model is a good logical flow of how one would think about the journey of understanding large language models. Let's dive into step three now. Step three is about inferring a decoder only large language model, which is have a trained large language model. We have to understand how this large language model selects a token when there are potentially multiple tokens that are possible at any given step. And we also want to study how to make those responses more creative. So now let's look at how text generation happens. So the first thing you need to do is provide the large language model with a prompt. Obviously, if you're just looking at the large language model, it will not start spitting out words, correct? So you have to ask it something. For example, you could ask it a question so that it can provide a response to that question, or you could give it a sentence so that it completes the sentence. So let's look at how that happens. So let's start with a prompt like this, where you say New York is that's my prompt that you can see in the bottom here. And we want the large language model to complete this sentence. Now, we studied how this is processed through the large language model already, but just as a quick recap, the first thing is you convert this into an S cross D matrix, which is a word embedding matrix that goes through the self-attention calculations, and the S cross D matrix now gets contextually updated. So the large language model will redistribute all the feature dimension values across all the tokens based on the context in which all of those tokens appear in this input sentence. So far, the tokens in the input sentence is just New York is the. Now that makes the journey forward. It goes through the feed forward neural network, and then now you have your final S cross D matrix. Now this S cross D matrix is projected using the linear projection layer to an S cross V matrix, because from this S cross V matrix, which is what we're going to be studying throughout the rest of this section of the presentation, you have for all the token slots, right? The S token slots, because that's your context window. For each slot, there is a possibility of picking a token from a maximum of V number of tokens, where V, which is this is here, V is the total number of tokens in your vocabulary. Now, using this framework, let's see how the trained large language model will start to fill up which token it feels is the right one for each of these slots. All right, so I'll use this part of the screen to show what goes into the large language model, and we'll use this part of the screen to see what it predicts as the next token. Now, in this S cross V matrix that you have here, obviously you don't have to predict the prompt tokens, because those are given as an input. So you see that the first four positions are occupied by the tokens that are there in your prompt. And for each of these positions, you say, for example, this position, this is new, this is York, this is, and this is the. So the next position is where the next token is going to be inserted, right? With one of the words from the vocabulary. Now, how is that done? This is made up of all these small numbers that are coming from the linear projection of the S cross D matrix to the S cross V matrix. That happens at this part of the LLM. Now, how do you pick one of these tokens? Well, you use softmax. So what is softmax? When you actually studied this in depth in other episodes, but just as a quick recap. So let's assume, just for the sake of making the picture more simple to understand, there are just three possible tokens in your vocabulary. And you have to use softmax to pick the one that is most likely. And through the calculations that happen through all these layers of the decoder-only LLM, let's say that each of those slots that you see here, let's say there are three here. So each of these slots is one value is 5.1, the other value is 2.4, and the third value is 7.8. Now, when you apply softmax, what softmax does is that it uses this formula here to turn this into a probability distribution table. And again, as I said, I've explained this in a lot of detail in season 1, episode 2, as well as in episode 3. So if you really want to go into the technical depth, you can go back and reference that. Season 1 again, episode 2 and episode 3. So this one, as I said, converts the raw logit values, which are the raw values that goes into these slots, into a probability distribution table. Now, obviously, if you're doing a probability distribution table, everything needs to add up to 1 or 100%, right? When this gets converted, we see that this token from the vocabulary has the highest probability of 0.933 or 90.3% probability that this is the right token that you are supposed to pick from the possible tokens in your vocabulary. Very good. So let's say that tokens happens to be financial and it has picked it with a 0.933 probability. Now, it could be anything, but the reason it is financial is because, again, through the process of training, this large language model has adjusted its weights so that it knows that the most likely token after New York is financial. There could be other tokens too, but they have a lower probability of appearance after the preceding tokens like New York is the. Very good. So now it has picked financial as its next token, right? Now you append financial to the input tokens. So New York is the financial now becomes your input, and then you pass it through the LLM again, and now it predicts the next token using the same strategy as capital. Now you pass this capital back as input. So New York is the financial capital. You pass all these tokens and it's off as the token with the highest probability. Following New York is the financial capital. And again, I'm noting the properties here of its prediction of that token at each of these time steps. Now the next time step you add off into the input and then it predicts United probability of 0.81, and then you add United back into the input, then it predicts states with a probability of 0.911, and then you add states back into the input at time step 6, it produces EOS or end of sequence, which means you're done with the prediction. So the sentence is complete now. So a couple of things. When does it know when to end its prediction? Well, one simple way is when it sees this special end of sequence token. But more realistically, the way it knows when to end it is based on number one. Is you say, I want you to produce no more than a certain number of tokens as my output, let's say 100. So it'll keep on generating till it sees 100, or it sees an end of sequence token and it terminates there. Remember, as one step, which is step 2, which is fine tuning. The fine tuning basically tells it when a question is asked, based on the type of question you ask, what is the type of result that needs to produce? And we'll actually study this shortly in a few slides down. So that's another technique. Instruction fine tuning tells the large language model when a question is asked to generate a response and when to stop. And so it has basically now produced this result. Given the input prompt, New York is the completed sentences, New York is the financial capital of United States. Very good. How did our model just all this model do? So there's a measure called perplexity. Now, this is a metric that quantifies how confused the large language model was when it is picking these tokens. That's the reason why it's called perplexity. How perplexed was it? And the formula for calculating that is actually very simple. So the perplexity of a generation can be measured as E over take the log of each of the probabilities of the tokens that it produced. So for example, it produced the first token financial with a probability of 0.933. So you take a log of 0.933. Then it produced a second token capital with a probability of 0.724. So you take a log of 0.724 and you add it to the previous one, 0.933. Then it produces a third token with a probability of 0.672. So you take a log of that and you add it, and so on. So you add up the log values of all the probabilities, and then you divide it by the total number of tokens that are produced. So it produced 6 tokens. You divide it by the total number of tokens, and you take a negative value of that, and you raise that value as a exponent e, and then you get a value of 1.38. Now, what does this 1.38 mean? Actually, what this means is that large language models, for each step on an average, could pick from between 1.38 tokens. So let's say we round it up. So it says that it could pick between 2 tokens. For example, New York is the one token could be financial. It's picked it with a 93% probability. The other token probably could have been something like most. For example, the sentence could have been completed as New York is the most populous city in the United States. It's also a valid sentence for framing, correct? So financial, it has picked, or it could also have picked from most as the other token. So on an average, it's saying that the large language model at each step had a choice between picking between 1.38, which is actually very good, which means that its predictions are pretty accurate. Imagine if at each step the large language model had 1,000 tokens to pick from. So which means that the large language model is now confused as to what is the right token and so on. So that's why Perplexity measures how confused or how perplexed the large language model is in picking tokens. Now, obviously, the lower the Perplexity score, the better it is. The prediction is much better because it means that at each time step, the large language model has fewer number of tokens to pick from, and as a result, it is less confused. Typically, a Perplexity score between less than 20 is supposed to be very, very good. State-of-the-art large language models get to a Perplexity of 20 and less. Average smaller large language model or trained with a very small sample set can do between 20 to 100. If you go past the 100 Perplexity score, which means that on an average at each step, the large language model had 100 possible tokens that it could pick from. It's considered to be a pretty bad or poorly trained large language model. Actually, the Perplexity score is not used during inference. It's typically used as an evaluation metric during the training step. But this tells you there is a way in which you can mathematically know how well the model is doing its predictions. By the way, just a fun fact, the AI company Perplexity gets its name from this evaluation metric. All right, so a few questions that come up here. I told you that there could be multiple tokens that it could pick from and multiple valid tokens, by the way. For example, if the prompt was the weather today is, and the potential valid tokens is the weather today is hot, or the weather today is cold, or unpredictable, or rainy, or pleasant, or balmy, or it could be anything. You could have multiple tokens that are valid as the next token based on the previous 4 tokens, the weather today is, correct? So how does the LLM figure out which of these tokens to pick? I show you this green box. After softmax, there is this green box called token selector. So what does this token selector really do? We'll study that next. But the other problem that you also want to understand is how do you make the LLM's responses more creative? For example, let's say the prompt I give is, she opened the, and I wanted to predict the next set of words after this. So one way of predicting is, she opened the door, which is a fully formed sentence, syntactically, semantically correct, it's good. But now, what if you want to, if you're, let's say you're writing a essay, right, or you're writing a novel, and you want the LLM to generate text which is more creative, right, more philosophical or something like that. So how do you tell a trained LLM that start to get a little more creative when you're picking next set of tokens? For example, a creative next set of tokens could be something like, she opened the doorway to a sea of new opportunities. So it's more creative, correct? So how do you make the LLM actually generate these creative responses? Now let's study both of these things. How does the token selector work? And how does the LLM become more creative? Let's start with understanding how the token selector works. So there are 5 techniques that can be used to select the next token. And I show you all the names of the 5 here: greedy sampling, top K sampling, nucleus or top P sampling, beam searching, and contrastive searching. We will study the first 3. So the first technique is called greedy sampling. Now the prompt is the weather today is, and you're filling the next word. Now let's say that out of the V vocabulary words, each of the words, after you do the softmax, the probability distribution turns to be something like this. So in greedy sampling, what you do is you basically pick that token which has the highest probability. So here the rainy has the highest probability of 0.3. So you pick that as the token. One of the advantages of a strategy like this is that it's very fast. You do a softmax and then you can do argmax, and it'll give you that token that has the highest probability and you're done with it. But the challenge with something like this is that the results are going to be very repetitive and predictable. You don't want that because Even humans would like to see variety. When humans are generating text and you ask me a question twice, let's say even a very simple question like, what is the capital of France? The first time around, I might answer with a single word, Paris. And you ask me the question again, what is the capital of France? And I might say, Paris is the capital of France. So usually, even the human mind is tuned to provide the same answer with more variety. So you want to mimic that, and greedy sampling does not give you that. It just gives you the standard set of tokens, very predictable. So this is not going to work. So what's the next strategy? So the next strategy is to top K sampling. So again, probability distribution after it goes through the linear projection is this for each of the tokens in the vocabulary. See, in top K sampling, what you do is that you sort all the tokens by the descending order of probability. So now you have sorted list. Rainy still happens to be at the top because it of course had the highest probability. Now what you do is that you pick top K tokens out of this. And it's a configurable parameter. Let's say the top K is 5, which means that you want variety. So at any given step, you can pick from the top K probabilities. So let's say here K is 5, so you pick from the top K. Next, what you do is that you add the probabilities of the top K. You add them up. So the probabilities of the top K are 0.3 plus 0.25, which is for unpredictable, 0.20 for the token cold, 0.10 for the token windy, and 0.05 for the token cloudy. You add them all up. So the total probability 0.90. Now what you do is that renorm top K by dividing with the summed probability. So that's nothing but you take rainy. What was its original probability? 0.30. You divide it by 0.90. So it becomes 0.33. You take unpredictable, what was its original probability of selection? 0.25. You take 0.25 and divide it by the total probability of the top K, 0.90, it becomes 0.28. So what you do is that you renormalize the top K this way. Now once you do a renormalization, at the time of generation, you generate a random number, a value between 0 and 1. Now, if the values that you generate is between 0.00 and 0.33, you pick rainy. If the value that you generate randomly is 0.33 and 0.61, you pick unpredictable. The value is between 0.61 and 0.83, pick cold. So how did, first of all, 0 to 0.33, you understand this one. Rainy had a renormalized value of 0.33, so that makes sense. Where did 0.61 come? 0.61 comes from 0.33 plus 0.28, which is the probability of the next token, which is 0.28. You add this up, you get 0.61. Where you get 0.80? Well, you add 0.61 plus 0.22, you get 0.83. So all of this, by the way, it's renormalized, but all of this add up to 1.0 or 100%. But when you renormalize and you get this, you are picking from these top K samples using this distribution. Now, even here, you notice that because this has the highest probability, it is still going to pick rainy most likely, but it also gives chance to the other tokens based on this new renormalized distribution. So now what you get as a pro is that you have balanced diversity of picking tokens. You don't get this repeatability, which is boring when it comes to filling out tokens or predicting the next set of tokens. That's a pro, but what's the challenge? The challenge is that how do you pick the top K? Is K5 good enough? Should I pick 10? Should I pick 20? What should be the total value of K? So there's no clear way to identify the total value of K. So that's one challenge at the top K. Now to fix this came the next strategy, which is called top P or Nucleus sampling. And by the way, Nucleus sampling is the technique that is used pretty much by most of the production grade large language models today. So the strategy is something similar with one twist. So what you do is that you sort all the tokens by descending order of probabilities like we did with top K. Now you have your probability distribution, all these tokens resorted. Now what is that? You pick the smallest number of tokens here whose cumulative probability is greater than some probability P. Let's say the probability P that you pick is 0.70, so 70%. So you start with the first token. What is the first token? You already sorted it out. So the first token's probability is 0.30. Very good. Is it less than this P that we selected, 0.70? Yes. So that becomes one of the candidates that you're interested in. Then you go and pick the next token, which with its probability of 0.25. Now you add 0.30 plus 0.25, which is 0.55. Is that less than the probability P that we picked, a configurable parameter, which is 0.70? It is. Fine. So even unpredictable makes it to your candidate list. Then you go to the next token after that, which is 0.20. So if you add 0.20 to this 0.55, it's 0.75. Now you see that 0.75 is greater than 0.70. At this point, you add cold and you stop. So now what you have done is you picked 3 tokens whose cumulative probability is 0.75, which exceeds your configurable probability that you're giving P, which was 0.70. Very good. We do the same thing. We renormalize this now again. We renormalize by taking these three candidates. Like Rainy had the original probability of 0.30. Well, you divide it by this cumulative probability that you got 0.75. You get 0.40, and you do the rest in a similar way. Now, the same strategy. You generate a random number while doing during inference run, a number between 0 and 1, and the random number that you pick is a value between 0 and 0.40. Then you pick any. If it is between 0.40 and 0.73, you pick unpredictable and so on. This produces more coherent and diverse text than top K because it still favors higher probability tokens, and it is still based on probabilities. At the end of the day, all of these things are probabilities. So it still uses the probability as a measure to figure out which tokens it will select as its candidate list. Again, the challenge still is that what do you pick as your configurable probability? Now that is, yes, that exists, but somewhat better than picking top K, because top K is just a numeric number. Here you're giving it a probability and say, hey, the cumulative probability is 0.7 or 0.75, which is 75%. I know that most likely those are good candidate tokens to pick. Again, the strategy is pretty simple to use, very easy to calculate, and hence this is the most popular strategy that is used as a token selector strategies by most of the production grade LLMs today. So now we showed you how an LLM can pick from multiple possible tokens during inference or during text generation time. It gives the feel of non-repeatability. It gives the feel of variety when answers are being generated by an LLM. Now let's look at how do you control the creativity of this LLM. Now, what you do is that, first of all, the top K or the top P techniques allow us to pick from a certain range of tokens based on the probability, correct? And using softmax. Now, influence the creativity. First of all, what is creativity? Creativity is, let's say you want to ask this question. The question is, explain what a queue data structure is, and you pass it to your decoder-only LLM, and you expect it to get an answer. Now, a regular answer could be a queue is a data structure that processes items in the order they arrive, enqueuing new elements at the back and dequeuing from the front. But now let's say you want the answer to be more formal, because you want to include that in some report that you're putting together for, let's say, your master's some assignment or something. So you say, I want a more formal answer. So you pass something. We'll see what that something is. So the LLM now produces an answer like, a queue is a linear data structure where elements are inserted and removed using the first in first out principle. What if you want to explain this thing to your grandma who does not understand computer science, and you want the LLM to produce an answer? We ask this question that, explain to me like I'm 5-year-old, or explain to me like I'm explaining to a child and whatnot. So you pass something to the transformer that will now swing the answers so that it produces more casual answers. For example, a creative casual answer could be the same question, explain what a queue data structure is. A creative answer is, a queue is like a patient line at the bakery. Newcomers join the end and customers are served from the front, ensuring orderly progression. Now, this is something that people who do not understand computer science can also understand, because they have been in queues or lines at a bakery or at a grocery store and so on. So how does the large language model end up doing these kind of things? For that, there is this another layer that you can insert called temperature. Now, the idea behind temperature is that, and by the way, temperature is used only during inference. It's not a training level layer. You take a trained LLM and then you insert this temperature layer, and it controls the diversity of the generated output. So let's understand what this temperature is and how does it actually work. So let's say that our vocabulary only has 4 words. Just to kind of make our understanding more solid and easy, let's start with small sizes. Let's say your entire vocabulary is made up of only 4 words. Now, the token that is being generated, let us say the logit value for the first token is -1, the logit value for the second token is 0, for the next token is 3, and the fourth token is 5. So when you softmax it, what do you get? You get these probability distributions. 0.2 for the first token, 0.6 for the second token, 11.8 for the third token, and 87.4 for the fourth token, correct? By the way, all of this, when you add it, goes to 100%. This is a standard softmax. There's nothing new. I'm sharing the same thing here. So these are the possible words from the vocabulary, and this is when you softmax it based on the final projection layers logits, you get this distribution. Now, let us say I'm using top P sampling, and my P that I've selected is 80%, which means that pick as many tokens from this possible 4, as long as the cumulative probability is greater than 80%. Well, it's going to pick the fourth token because its probability is 87.4%. Now, what we want to do is that we want to get more creative. And when you want to get more creative, you have to relax this thing where more tokens starts to get into this candidate list of tokens that can be picked. That's how creativity is found. Creativity is found by picking not the most statistically highest occurring next word, but also some other word that could have a lower probability statistically, because there are not too many such tokens as the next token in your training data set, but it is still a valid next token because creative answers are fewer than non-creative answers. So there are some valid tokens, but whose statistical appearance, the probability of appearance is lower. So you want to allow those things also to start showing up in the candidate list. And the way you can do that is by increasing or decreasing their probability of getting picked. Correct? That's where temperature. So what temperature does is that it takes a standard softmax formula, which this is the softmax formula, and just by making one very very small change, which is you divide the probability of each token by this number t. This number t is a configurable parameter, which is what is called as a temperature parameter. I'll explain to you why shortly why it's called temperature. Let's say the temperature is 10. So what you do is that you take the logit values that you got from the from the final layer, you divide it by the value t here. Let's say t here is 10. So for example, the logit value for the first token is -1. So you take -1 divided by the temperature t, and then you divide that by the summation of all the logit values, again by dividing by 10 here. So -1 divided by 10, 0 divided by 10, 3 divided by 10, 5 divided by 10. 10 again is our temperature that we have selected, correct? Now once you do this and then you apply softmax, you see that the probabilities got changed. Now again, let's apply the top p sampling with the probability of p being 80%. So cumulatively pick all the tokens. When you add them up, the cumulative probability should be greater than 80%. You see that more tokens now start to get picked. Now let's do one more run. Now let's pick a temperature which is very low, 0.1. Now when you do this, what happens is that again -1 divided by 0.1 divided by this number here, again 0 divided by 0.1, 3 divided by 0.1, and so on. Now once you do that and you do the softmax, you see that all the probabilities now got distributed to that token which already had high probability. So when you lower the temperature, it minimizes or it decreases the candidate list of tokens that it can pick from. Now, what this table tells you is that just by dividing the logit value with the temperature value, and you picking the temperature here, higher the temperature, what you do is that the distribution of the probabilities goes more towards other tokens. Lower the probability, the distribution of probabilities now goes to a fewer number of tokens, as you can see here, right? Without doing any temperature, the temperature is 1, which is the standard softmax formula. So it is this. Now, if you increase the temperature, you see that more tokens start to get picked, purely based on the math here. If you decrease the temperature, you go to from 1, which is the default, to let's say 0.5 or 0.1. As you can see, the probabilities from the other tokens start to be given to the token that already had higher probability, right? When you increase the temperature, the probability from the higher tokens now slowly start to get to those tokens that have a lower probability also. Now, you're using temperature as a way to increase or decrease the total number of potential candidates that it can pick from. Again, using the standard top P or top K or whatever sampling technique, but you increase the candidate list just by changing the probabilities. So how does temperature actually get passed? Because when you're using ChatGPT, you don't say, I want you to generate responses at this temperature. Actually, the LLM, the chat application, figures this out automatically. For example, when you ask it a question, it will classify the question and it says, hey, if the question that is being asked is factual in nature, which is historical fact, like who is the first person to walk on moon, a math problem like what is 5 plus 2, a general knowledge question like what is the capital of India, or technical question like what are the 3 laws of thermodynamics. It's a factual question and you don't want the responses to be creative. So what it does is that it will start to make the temperature value less than 1, smaller temperature value. So, which means that fewer tokens start to end up being in the candidate list that the top P sampling can pick from. Now, let's say you ask an open-ended query, a query like storytelling, write a short story about a robot discovering emotions, or brainstorming ideas like what are some innovative ways to use robots at home, or creative writing like imagine a day where humans can communicate with animals, what would they say to them, or philosophical questions like what would society look like if you abolish wokeism completely, right? So there it knows that it can classify the question as, oh, what the user is trying to ask for something that is more open-ended, so I can be more creative. So what it will do is that when it is invoking the large language model to generate tokens, it will pass a higher temperature. So you don't really have to pass it yourself. This is inferred from the question you're asking, and the large language model automatically does it behind the scenes. So the question that comes up, you're curious, is why is it called temperature? Well, The reason it's called temperature is that you can actually go back to thermodynamics to understand this. So let's say that you have three boxes here and particles are going in these boxes, and you have a dial that can increase or decrease the temperature. Now, let's say this is the window. Observe how many particles I see within that window, which is your like the top P sampling. I'm picking anything that is greater than 75%. So if you take this analogy of these particles in a box where you're giving more heat, what you see is that when you increase the heat, the particles will start to go more apart, correct? This is just the law of thermodynamics, right? You increase the heat, they start to go disperse more away from each other, which means that if you're peeking through this window or top window using your analogy, you'll actually start to see more tokens in that window. Why? Because temperature is higher, these particles are more separated from each other. Now, as you're decreasing the temperature, let's say you get it to room temperature, you'll see that these particles start to come closer towards each other. Now, when they start to come towards each other, you'll see that if you're peeking through the same top P window here, you'll see that fewer number of tokens start to appear. Now let's say dial the temperature down even further. You make it colder and colder. Then you see that, these particles start to come more closer to us. It's almost like, you take liquid water, room temperature, you heat it up, increase the temperature, it becomes steam. So the particles are out, it's in gaseous state. Now you take liquid water at room temperature and then you cool it. Then what happens is it starts to become like ice, which means that the water molecules are getting closer to each other. So when something like that happens, again, when the temperature is lower and you peek through this window again, the top view window, you'll see that, because more particles are closer to each other, very few will show up in the top view, that window, correct? So the inspiration for temperature in large language model comes from thermodynamics. So now that we have studied step 1, which is pre-training, and step 3, which is generating responses, let's look at step 2, fine-tuning. So what exactly is instruction fine-tuning a pre-trained large language model? So let me explain that using an example. So let's say the question that you ask an LLM is, what is the capital of India? And now let's say you were to ask this question to just a pre-trained large language model. Now it will start to produce text like this. It will say India's capital is New Delhi, which lies in the northern part of the country and has long been at the heart of Indian governance, serving not only as the administrative capital, and so on and on and on and on. It will keep generating all legitimate, syntactically, semantically correct words, but the answer is going to be really long because it does not know that a question like this can be answered just with maybe one single sentence or just two words in this case, right? So, how do you make this pre trained large language model actually understand that? The way you do that is that you take your pre trained large language model and then you do what is called as instruction fine tuning. And when you fine tune it, and when you ask the same question to this fine tuned model, instead of rambling on and on with a lot of words, it is going to produce concise responses to questions like this. So a fine-tuned large language model will answer the question, what is the capital of India, either with just two words, New Delhi, or something like the capital of India is New Delhi. So how do you make this pre-trained large language model respond back this way? The way you do that is you take this pre-trained large language model and you do this thing called instruction fine-tuning. And what is instruction fine-tuning? Instruction fine-tuning is actually a supervised training of a pre-trained large language model. Remember that in pre-training, you're doing completely unsupervised. You're just downloading the text from wherever you can, the internet crawl and all that, and you're feeding it as is. But in instruction fine-tuning, because you want the responses from this pre-trained large language model to be aligned to how the human wants to see the responses, to do that, you have to essentially give the pre-trained large language model a instruction and a response pair, which is human created training data set of millions of these instruction response pairs that you pass to this pre-trained large language model. And I'll show you the format for that shortly. There's another type of fine tuning, which is called reinforcement learning based on human preferences. Now, while an instruction fine-tuned large language model can just answer questions with very terse, concise, specific responses, sometimes you want to also ensure that these responses are aligned to human preferences. For example, if somebody were to ask a question that could be answered in a terse way, but the response is pretty dangerous. Let's say somebody were to ask this question, I'm feeling really lonely and down right now. And you don't want the instruction fine-tuned large language model to propose solutions that could be harmful to this individual, right? So you want to further fine-tune a instruction fine-tune model based on human preferences. So that is called as reinforcement learning based on human preferences or human feedback. So that's another type of fine tuning. Now, there's a third technique, which is actually not a fine tuning strategy, but it is an optimization model called parameter efficient fine tuning. So, this is a way in which you can decrease the time it takes to do instruction fine tuning or RLHF based fine tuning. So, that's another strategy of doing fine tuning. So, it's called PEFT. Parameter efficient fine tuning. So, what is instruction fine tuning? Instruction fine tuning actually is pretty simple. As I said, it's a supervised training where you provide multiple instructions to as your training data set. Instructions could be something as simple as it starts with this special keyword called instruction, and you as a training sample you give it a question, and for input you can just leave it as empty, and for response you say what is the response for that. Like for example, instruction is what is the capital of India, response is New Delhi. What is the capital of United States, response is Washington DC. So those kind of things, you give it like thousands or millions of such instructions. Or instructions can be more complicated, things like summarize the following text in 2 sentences, and the input will be this entire big blob of text, and the response you'll show what would be the human generated summaries for this huge blob of text. And because the instruction says in 2 sentences, you would actually just give 2 sentences in your response. Or instruction could be things like classify the sentiment of this review as positive, neutral, or negative, and you give it a review and then you provide a response. So again, as you can see, the idea here is that you are exposing your large language model to how a question needs to be answered. This is how the human wants. Alignment between the question and its response should be in this format. Now, a large language model can see millions of these instructions and then it can learn this thing automatically. So the human effort here is in not providing all these rules. The human effort is just exposing or showing to this large language model that if I were to give you an instruction that looks like this, and if this were the optional input that I give you along with the instruction, this is the type of response I want, and I'm going to give you millions of such examples so you learn from it. That's all instruction fine tuning is. And you can go online and you can actually see several of these sample instructions. I'm showing you something from the Instruct GPT paper. This is how the instructions look like when they were training the first ChatGPT. By the way, there is the Stanford, there's a very nice data set called Alpaca data set, which shows you how do you construct these instructions. For example, in the inner circle, you see the instructions can be something like generate, and generate what? Generate a list, generate a sentence, generate a story, generate a question. Or it could be things like rewrite, and then you can give it a sentence or a statement, or something like summarize, and then you could give it an article, text. So there is a format that they have described saying that what you could actually construct massive instruction fine-tuning data set using something like this. I will not go into all those details right now because I think already this video is very long. Fine tuning itself is a very vast subject. We'll cover all those details in another episode. Just suffice it to say that in practical sense, when you want to fine tune, you actually want to be cognizant about the time it takes to fine tune and the cost incurred to do the fine tuning. There are several toolings that are available that you could use to bring down the cost of fine tuning and also make it more faster. We will cover all of those things in subsequent episodes because this episode is already too long. All right, so where do you go from here? So we have studied in this episode pretty much in depth how a large language model learns languages, how that large language model can be used to answer questions, how it produces text, and all of those things. So where do we go from here? As I said, generative AI is a very, very vast field. It's a very new field, but the rate of progress has been tremendous. In fact, I have never seen anything that has grown this fast, this quickly. So what we will cover in subsequent episodes, now that you have a very solid foundation, is things like model architecture enhancements. At the very beginning of this episode, I told you that in 2024 and onwards, there's been research in enhancing the model itself, things like multi-head latent attention, things like mixture of experts, speculative decoding. I will cover all those in another episode. How do you actually do this fine-tuning and further, right, for things like reinforcement learning from human preferences. I'll teach you different policy optimization techniques, PPO, GR, and so on. Then we'll go into this fine-tuning strategies, parameter efficient fine-tuning strategies like LoRa, quantization. Now, how do you parallelize this fine-tuning or training across multiple GPUs and a cluster of servers and all of those things? We'll study that. We'll also study optimizations during inference. That's actually an active field of research because You might train for, let's say, 20% of the time, but you would use your model 80% of the time for inferencing. So there's a lot of work that can be done in terms of optimizing your inferencing, both for performance as well as bringing down cost. So I'll talk about strategies like pre-fill strategies, decode strategies. I'll talk about key value management, techniques like flash attention, the key value caching, page attention strategies, and how do you actually manage the GPU for concurrent serving? What if you have thousands of users hitting your large language model during inference? How do you do that? How do you make your large language model call tools? For example, if you're giving it a math problem, you wanted to call a calculator tool as an example. How do you do that? So there's so much of other interesting topics that we could study. But I think this episode gives you a solid foundation to understand how generative AI works, and we can build on this foundation in subsequent episodes. So until next time, thank you very much and happy learning. If you like this video, please subscribe to my channel, like it, and share it with others. Happy learning. Thank you very much.